Climate Change and Water Management. Table of Contents. Introduction. Climate Change and the Global Water Crisis. Chapter 1. Understanding Climate Change. Chapter 2. Water Systems and the Hydrological Cycle. Chapter 3. Impacts of Climate Change on Water Resources. Chapter 4. Droughts, Floods, and Water Extremes. Chapter 5. Water Security and Human Well-Being. Chapter 6. Climate Change and Water Governance. Chapter 7. Innovations in Water Management. Chapter 8. Financing Water in a Changing Climate. Chapter 9. Education, Engagement, and Behavior Change. Chapter 10. The Future of Water Management. Chapter 11. Case Studies in Water Management. Chapter 12. The Role of Policy and Governance in Shaping the Future of Water. Chapter 13. The Role of Education and Advocacy in Water Conservation. Chapter 14. Future Innovations in Water Technology. Chapter 15. Global Collaborations and International Cooperation in Water Management. Chapter 16. The Role of Technology in Global Water Management. Chapter 17. Policy and Governance for Global Water Sustainability. Chapter 18. Community-Based Water Management. Chapter 19. Water Education and Public Awareness. Chapter 20. Innovative Water Technologies. Epilogue. The Path Forward. Introduction. Climate Change and the Global Water Crisis. Thousands have lived without love, not one without water. W.H. Auden. Water is the lifeblood of our planet. It shapes landscapes, supports ecosystems, and sustains human life. Yet, as the 21st century unfolds, the world faces an unprecedented water crisis, one that is being amplified by the accelerating forces of climate change. Across continents, the rhythms of rain, snow, and seasonal flows that have governed life for millennia are becoming less predictable. Glaciers that feed rivers are shrinking. Groundwater tables are falling. Droughts are deepening, and floods are becoming more frequent and more destructive. From megacities to rural farmlands, communities are grappling with water insecurity at a scale and speed never before seen. The worsening water picture. Today, over 2 billion people live in regions under high water stress. Rivers such as the Colorado, the Ganges, and the Murray-Darling are struggling to meet the demands of agriculture, industry, and growing urban populations. Lakes like Chad, Urmia, and the Aral Sea have shrunk dramatically. Groundwater aquifers in countries like India, China, and the United States are being depleted faster than they can be replenished. This crisis is not driven by climate alone, but climate change acts as a powerful stress multiplier. It aggravates the challenges posed by poor infrastructure, weak governance, population growth, and unsustainable consumption. Climate change, a threat multiplier. As global temperatures rise, the water cycle is becoming more intense and erratic. Warm air holds more moisture, which leads to heavier rainfall in some areas and more prolonged drought in others. Sea level rise threatens freshwater sources through saltwater intrusion. Melting snowpacks and glaciers disrupt downstream water supplies. The timing and distribution of water are changing faster than our management systems can adapt. In many ways, the story of climate change is a story about water, too much, too little, or too polluted. Why water management is central to climate resilience. Effective water management sits at the heart of climate adaptation. Whether we're talking about ensuring food security, preventing waterborne diseases, or supporting resilient cities, managing water wisely is critical. It connects to nearly every sector: energy, health, transportation, biodiversity, and industry. Yet, traditional approaches to water planning, based on past climate data and static assumptions, are no longer sufficient. The systems we designed in the 20th century must be reimagined for the uncertainties of the 21st. What this book will explore. This book offers a comprehensive exploration of the relationship between climate change and water management. It examines the science, impacts, and strategies needed to ensure water security in a warming world. Through global examples and practical insights, we will look at the science behind the hydrological impacts of climate change, how water scarcity and excess manifest across different geographies, the intersection of water with agriculture, cities, and energy, case studies of successful water adaptation from around the world, innovative tools, technologies, and policies for sustainable water use. We also acknowledge the ethical and justice dimensions of the crisis. Vulnerable populations, often least responsible for greenhouse gas emissions, are disproportionately affected by water-related climate impacts. Building water resilience is not only a technical challenge, but a moral imperative. A call to act. We are at a crossroads. If managed wisely, water can be a source of peace, prosperity, and sustainability. If neglected, it can fuel conflict, poverty, and ecological collapse. This book is written for students, policymakers, water managers, and concerned citizens who recognize the urgency of the water-climate nexus. It is both a diagnosis and a blueprint, a call to understand, to adapt, and to act. The future is not yet written. The decisions we make today about how we value, use, and protect water will ripple through generations to come. Chapter 1: Understanding Climate Change. We are not only facing an environmental crisis, we are facing a crisis of perception, of values, and of action. What is climate change? Climate change refers to long-term shifts in temperature, precipitation, wind patterns, and other elements of Earth's climate system. While the climate has always varied naturally over time, the changes we are witnessing today are largely driven by human activity, particularly the burning of fossil fuels like coal, oil, and natural gas. These activities release greenhouse gases, GHGs, into the atmosphere, primarily carbon dioxide, methane, carbon tetrahydride, and nitrous oxide, dinitrogen monoxide. These gases trap heat and prevent it from escaping into space, leading to a gradual warming of the planet, a phenomenon known as the greenhouse effect. The scientific consensus. The scientific consensus is clear and robust. Reports by the Intergovernmental Panel on Climate Change, IPCC, based on the work of thousands of scientists from around the world, confirm that human influence is the dominant cause of observed warming since the mid-20th century. Key findings from the IPCC's Sixth Assessment Report, 2021, include: global temperatures have risen by approximately 1.1 degrees Celsius since pre-industrial times. Sea levels have risen by over 20 centimeters since 1900, with the rate accelerating in recent decades. Glaciers and Arctic sea ice are shrinking rapidly. Extreme weather events, such as heat waves, floods, and droughts, are becoming more frequent and intense. These changes are not projections, they are already happening. Climate versus weather. A common confusion is the difference between climate and weather. Weather describes short-term atmospheric conditions, e.g., a rainy day or a hot afternoon, while climate refers to long-term trends and averages, typically over 30 years or more. For example, a snowstorm in February doesn't disprove global warming. Rather, what matters is whether snowstorms are becoming more or less common, and whether winter temperatures are trending upward over decades. Key drivers of climate change. The primary causes of human-induced climate change include fossil fuel combustion. Energy production, transportation, and industry are major sources of carbon dioxide. Deforestation. Trees absorb carbon dioxide. When forests are cut down, carbon is released, and fewer trees remain to capture emissions. Agriculture. Methane from livestock and rice paddies and nitrous oxide from fertilizers contribute significantly. Industrial processes, cement production, chemical manufacturing, and waste management all emit greenhouse gases. These activities have dramatically altered the composition of Earth's atmosphere in just a few centuries. Climate change feedback loops. Climate systems are interconnected, and small changes can trigger larger effects through feedback loops. Some major feedbacks include melting ice and reduced albedo. Ice reflects sunlight. As it melts, darker land and ocean surfaces absorb more heat, accelerating warming. Permafrost thawing. Thawing permafrost releases methane, a potent greenhouse gas, into the atmosphere. Ocean warming and acidification. Warmer oceans absorb less carbon dioxide and can release stored heat and gases back into the atmosphere. These feedbacks can make climate change nonlinear and unpredictable. Impacts across systems. Climate change is not just about temperature. It affects virtually every Earth system. Ecosystems. Many species are shifting their ranges or facing extinction. Food systems. Crop yields are impacted by drought, heat, and shifting growing seasons. Human health. Rising temperatures lead to more heat stress, the spread of diseases, and mental health strain. Economies. Damage from climate-related disasters is increasing yearly, especially in vulnerable regions. And critically for this book, climate change disrupts the water cycle, altering how water is stored, distributed, and accessed. Climate, justice, and vulnerability. Climate change is deeply unequal in both cause and effect. The global north, historically responsible for the majority of emissions, often has more resources to adapt. Meanwhile, the global south, least responsible but most exposed, faces the harshest consequences. Women, indigenous peoples, and low-income communities are often hit hardest, despite contributing least to the problem. Addressing climate change, therefore, is not just an environmental issue, it is a matter of justice. Climate action, mitigation, and adaptation. Responding to climate change involves two main strategies. Mitigation, reducing emissions to slow or stop climate change, e.g., renewable energy, carbon pricing, reforestation. Adaptation, adjusting systems to cope with the effects of climate change, e.g., building seawalls, improving irrigation, diversifying crops. Both are necessary. Even with deep mitigation, some climate impacts are now unavoidable, making adaptation especially urgent in the water sector. A systems approach. Climate change cannot be addressed in isolation. It is interconnected with food systems, energy choices, land use, technology, and political structures. Effective solutions require a systems approach that considers cross-cutting impacts and co-benefits. In this book, water is the lens through which we explore these connections. Because where water goes, so goes life, health, food, and conflict. Chapter 2: Water Systems and the Hydrological Cycle. Water is the driving force of all nature. Leonardo da Vinci. Water is everywhere, flowing through rivers and streams, locked in glaciers and snow, drifting in the clouds above, and buried deep underground. The complex journey that water takes as it cycles through the environment is essential to life on Earth. To understand the impacts of climate change on water, we must first understand how the hydrological cycle works and the key systems that store, move, and distribute water. The hydrological cycle. An overview. The hydrological cycle, or water cycle, describes the continuous movement of water within the Earth and atmosphere. It is a closed system, meaning no water is gained or lost, but it is constantly changing states, from liquid to vapor to ice, and shifting locations. The main processes in the cycle include evaporation. Water changes from liquid to vapor, primarily from oceans, lakes, and rivers. Transpiration. Plants release water vapor through their leaves, a process known collectively with evaporation as evapotranspiration. Condensation. Water vapor cools and forms clouds. Precipitation. Water falls to the Earth's surface as rain, snow, sleet, or hail. Infiltration. Water seeps into the ground, replenishing groundwater aquifers. Runoff. Water flows over the land, entering rivers, lakes, and oceans. These processes are powered by solar energy and regulated by temperature, land cover, vegetation, and topography. Key water reservoirs. Water exists in different forms and in various storage locations, or reservoirs, each playing a unique role in the hydrological cycle. 1. Oceans. Covering over 70% of Earth's surface, oceans hold about 97% of the planet's water. However, this is saltwater, unsuitable for most human uses without desalination. 2. Ice and snow. Roughly 2% of Earth's water is frozen in glaciers, ice caps, and snowfields, primarily in Antarctica and Greenland. These store fresh water, often releasing it slowly into rivers and streams as they melt. 3. Groundwater. Stored in aquifers beneath the Earth's surface, groundwater accounts for about 30% of freshwater used by humans. It can take years or even centuries to recharge. 4. Surface water. Rivers, lakes, wetlands, and reservoirs are vital for drinking water, agriculture, and hydropower, yet they contain only about 0.3% of global freshwater. 5. Atmospheric water. The smallest reservoir, water vapor in the atmosphere, is short-lived but critical in distributing water through precipitation. The natural balance. In a stable climate, the hydrological cycle maintains a delicate balance. Rainfall replenishes rivers and aquifers, snowpacks melt gradually to feed ecosystems and agriculture, and wetlands buffer floodwaters and store nutrients. But this balance is vulnerable. Even small shifts in temperature or precipitation patterns can disrupt the timing, quantity, and quality of water available for human and ecological needs. Water as a connector. Water connects everything. It links land and sky, ecosystems and economies, upstream and downstream communities. It is central to ecosystems. Wetlands, rivers, and lakes support biodiversity and provide essential services. Agriculture, irrigation, and rain-fed farming depend on predictable water flows. Energy, hydropower is a major renewable energy source. Cooling water is critical for thermal power plants. Health, clean water prevents disease. Poor sanitation causes illness and death. Understanding these connections is key to designing resilient water systems. Natural water variability. Water availability naturally varies by geography. Some regions, e.g. rainforests, receive high rainfall. Others, e.g. deserts, are naturally dry. Seasonality. Monsoon cycles, snowmelt patterns, and wet-dry seasons govern water supply in many regions. Year-to-year climate patterns. Events like El Niño and La Niña alter precipitation and temperature, causing droughts and floods globally. Climate change doesn't just add to this variability, it pushes it to new extremes and alters long-standing patterns. Human alterations to water systems. Beyond climate, humans have reshaped water systems in profound ways. Dams and reservoirs have transformed river flow, providing benefits like electricity and water storage, but often with ecological and social costs. Irrigation consumes 70% of global freshwater withdrawals. Urbanization increases impermeable surfaces, reducing infiltration and increasing runoff and flood risk. Pollution from agriculture, industry, and households degrades water quality, harming both people and nature. These interventions have increased water availability in some cases, but often at the expense of long-term sustainability. How climate change disrupts the cycle. Climate change is altering each stage of the hydrological cycle. Evaporation increases with warming temperatures, drying out soils and reducing water storage. Precipitation becomes more intense in some places and scarce in others. Snow and ice melt earlier or more rapidly, changing river flow patterns and reducing natural storage. Extreme events like droughts and floods are becoming more common and severe. Sea level rise threatens freshwater aquifers in coastal regions through saltwater intrusion. These disruptions mean water is increasingly out of sync with the needs of people, agriculture, and ecosystems. The challenge ahead. To manage water wisely in the age of climate change, we need to understand where, when, and how water is available. Protect natural systems that regulate and store water, like forests, wetlands, and aquifers. Develop flexible, adaptive water infrastructure and policies. Recognize that water security is climate security. Chapter 3. Impacts of climate change on water resources. Climate change isn't just about melting ice caps, it's about melting certainty in our water future. Climate change is altering how water moves, where it is stored, and who has access to it. Across the planet, the hydrological cycle is being thrown out of balance. The changes we now observe are not uniform. Some regions are becoming wetter, others drier. But the common thread is increased unpredictability, stress, and risk. This chapter explores the core ways that climate change affects water quantity, quality, timing, and distribution, with attention to both physical systems and social consequences. Shrinking glaciers and snowpacks. Mountains serve as water towers for billions of people, storing precipitation as snow and ice, then gradually releasing it during warmer months. Climate change is accelerating glacier retreat and reducing snowpack accumulation, disrupting this slow-release mechanism. Himalayas. Glaciers feeding rivers like the Indus, Ganges, and Brahmaputra are retreating rapidly. Over 1.5 billion people depend on these flows. Andes and Alps. Shrinking glaciers threaten water supplies for agriculture and hydropower. Rocky Mountains. Snowmelt timing is shifting earlier in spring, creating mismatches between water supply and demand. Loss of glacial mass not only reduces long-term water availability, but also contributes to glacial lake outburst floods, GLOFs, sudden destructive floods caused by unstable meltwater lakes. Altered rainfall patterns. Climate change affects the amount, intensity, and distribution of precipitation. In many regions, rainfall is becoming less reliable and more extreme. Sub-Saharan Africa. The Sahel has experienced alternating decades of severe drought and intense rains, affecting food and water security. South Asia. Monsoons are becoming more erratic, with longer dry spells punctuated by sudden heavy downpours. North America. Parts of the U.S. West are experiencing multi-decade megadroughts, while other areas face historic floods. Increased rainfall intensity leads to more surface runoff and less groundwater recharge. Conversely, reduced rainfall creates chronic water scarcity, affecting agriculture, hydropower, and ecosystems. Increasing drought frequency and severity. Droughts are becoming more frequent, prolonged, and intense in many parts of the world. These climate-enhanced droughts have cascading impacts. Soil moisture declines, reducing crop yields and increasing desertification. Reservoirs and rivers run dry, limiting irrigation and drinking water supplies. Aquifers are overdrawn, often beyond sustainable limits. Examples include California. A persistent drought has led to strict water restrictions and agricultural losses. Horn of Africa. Multiple failed rainy seasons have created humanitarian crises for millions. Australia. The Millennium Drought, 1997 to 2010, drastically reshaped water policy and management. Droughts are particularly dangerous because their effects accumulate slowly but last long, and recovery can take years. More frequent and intense floods. While some regions dry out, others face the opposite problem, flooding. Warmer air holds more moisture, increasing the potential for extreme rainfall events and flash floods. South Asia. Bangladesh, India, and Pakistan experienced devastating floods during monsoon seasons, displacing millions. Europe. In 2021, parts of Germany and Belgium faced once-in-a-century floods due to intense rainfall over saturated soils. United States. Hurricane Harvey 2017 dumped over 60 inches of rain on Texas, fueled by warm Gulf waters. Urbanization compounds flood risk by reducing natural drainage and increasing surface runoff. Climate-induced sea level rise also worsens coastal flooding, especially during storms. Rising sea levels and saltwater intrusion. As global temperatures rise, melting glaciers and thermal expansion of seawater are causing sea levels to rise, a threat to low-lying coasts and island nations. Consequences include saltwater intrusion into coastal aquifers, making freshwater supplies undrinkable. Loss of wetlands and estuaries, which act as natural water filters and flood barriers. Increased risk to infrastructure and agriculture in coastal areas. Regions like the Mekong Delta, Nile Delta, and Bengal Basin are already experiencing the intrusion of saltwater into farmland and freshwater systems. Water quality degradation. Warmer temperatures and altered runoff patterns degrade water quality in several ways. Algal blooms thrive in warm, nutrient-rich waters, reducing oxygen and harming aquatic life. Pathogen survival increases, raising the risk of waterborne diseases like cholera. Sediment and pollutant loads rise due to heavier rainfall, washing contaminants into rivers and lakes. Water treatment becomes more difficult and expensive as source water becomes more polluted or erratic in supply. Ecosystem disruption. Aquatic ecosystems are highly sensitive to changes in flow, temperature, and timing. Climate impacts include drying wetlands, which are critical habitats and carbon sinks. Declining river flow, which affects fish migration, especially for species like salmon. Shifting aquatic species ranges, threatening biodiversity. When ecosystems lose their natural hydrology, the services they provide, like water purification, flood control, and habitat, diminish or disappear. Social and economic consequences. The disruption of water resources leads to wide-ranging human impacts. Food insecurity from reduced agricultural productivity. Energy shortages where hydropower is a major source. Public health crises due to contaminated water and poor sanitation. Migration and conflict as people are forced to leave water-stressed regions. Water scarcity is increasingly cited as a national security concern, particularly in transboundary river basins like the Nile, Tigris, Euphrates, and Indus. Unequal impacts. Not all communities are affected equally. Vulnerable populations, especially women, indigenous groups, and the rural poor, often bear the brunt of climate-related water stress. Their access to decision-making, financial resources, and adaptive technologies is often limited. Adaptation strategies must therefore be inclusive, equitable, and locally informed to be effective. Summary: a shifting water landscape. Climate change is reshaping the global water landscape. What was once reliable is now erratic. What was once abundant may become scarce. These changes demand a fundamental rethinking of how we manage water, both in policy and practice. Chapter 4: Droughts, Floods, and Water Extremes. Water has no enemy, but mismanaged, it can drown a nation or starve a continent. Climate change is reshaping the extremes of the hydrological cycle. Across the globe, we're seeing longer, deeper droughts and more intense, frequent floods. These are no longer considered rare anomalies, they are becoming the new normal. Water extremes threaten human life, infrastructure, economies, and ecosystems, often simultaneously and disproportionately. This chapter explores the science, examples, and consequences of climate-driven droughts and floods, and how societies can better prepare for these growing threats. A warmer world means wetter and drier extremes. Why does climate change lead to both droughts and floods? The answer lies in how warming affects the atmosphere and hydrological cycle. Higher temperatures increase evaporation, drying soils and intensifying drought. Warmer air holds more moisture, about 7% more per 1 degree Celsius increase, leading to more intense rainfall. Weather patterns are becoming more erratic, with blocked jet streams and slower-moving storms prolonging extreme conditions. This leads to hydrological whiplash. A single region may swing from drought to flood in a matter of weeks or months, straining systems built for stability. Droughts, the slow-burning crisis. Unlike floods, droughts develop gradually but can last for years and leave deep scars. Types of drought. Meteorological drought, a period of below-average precipitation. Agricultural drought, when soil moisture is insufficient for crops. Hydrological drought, low river flows or declining groundwater and reservoir levels. Socioeconomic drought, when water scarcity disrupts society and economy. Global drought hotspots. The Horn of Africa suffered 5 consecutive failed rainy seasons, 2020 to 2023, leading to famine and displacement. California and the U.S. Southwest, experiencing the worst megadrought in 1,200 years. Southern Europe, rivers like the Po, Italy, and Tagus, Spain, Portugal, hit record lows in 2022-2023. Impacts of drought, crop failure, and food insecurity. Water shortages for drinking and sanitation. Wildfires, exacerbated by dry vegetation. Conflict over shared resources, especially in transboundary basins. Floods from deluge to disaster. Floods occur when water overwhelms natural or human-made systems. They are among the most deadly and costly climate disasters. Types of floods. Riverine floods, caused by sustained rainfall or snowmelt. Flash floods, sudden intense storms that overwhelm drainage systems. Urban floods, driven by impervious surfaces and poor stormwater management. Coastal floods caused by storm surges, sea level rise, or cyclones. Recent extreme flood events. Pakistan 2022. Unprecedented monsoon rains submerged 1/3 of the country, displacing over 30 million people. Germany and Belgium 2021. Record rains led to flash floods that killed over 200 people. Mozambique, Cyclone Idai 2019. Torrential rains and storm surge devastated infrastructure and livelihoods. Impacts of floods. Loss of life and property. Infectious disease outbreaks, e.g., cholera, leptospirosis. Damaged crops and food storage. Long-term economic recovery challenges. Compound events and cascading risks. Floods and droughts rarely act alone. Increasingly, we face compound risks when multiple extremes interact. Drought followed by floods can worsen erosion and water contamination. Back-to-back disasters can cripple disaster response and recovery capacity. Heat waves and drought together can collapse power and food systems. Cascading failures across water, energy, food, and health sectors require new thinking in risk planning and response. Infrastructure under strain. Water infrastructure was designed for a more stable climate. Under pressure from extremes, it is increasingly vulnerable. Dams and levees face overtopping or failure from extreme floods. Irrigation systems struggle during prolonged drought. Stormwater systems in cities are overwhelmed by intense rainfall. Groundwater pumps overdraw aquifers, leading to land subsidence. Aging and underfunded infrastructure cannot cope with these new stressors without significant adaptation and investment. Social vulnerability and inequity. Water extremes amplify existing inequalities. Low-income and informal communities are more exposed to flooding and lack insurance or adaptive infrastructure. Rural farmers may have no alternatives during drought but to sell assets or migrate. Women and children often bear the burden of collecting water during shortages or face increased health risks. Resilience must be built not just in systems, but in social protection, governance, and equity. Early warning and preparedness. Effective early warning systems are vital for saving lives and reducing losses. Drought forecasting relies on satellite data, soil moisture monitoring, and seasonal climate models. Flood alerts can be issued hours to days in advance with real-time rainfall and river level data. Community preparedness, education, drills, communication is just as important as technology. Investments in hydrometeorological services and local capacity are among the most cost-effective climate adaptation tools. Nature-based solutions. Engineered defenses are important, but nature-based solutions offer sustainable resilience. Wetlands act as natural flood buffers and recharge aquifers. Forests reduce erosion and slow runoff. Green urban spaces help absorb rainfall and reduce heat. These solutions are not only adaptive, they also deliver co-benefits like biodiversity, carbon storage, and recreation. Toward climate-resilient water management. Addressing water extremes requires a shift from crisis response to risk reduction. Integrated water resources management, IWRM, must account for climate uncertainty. Flexible infrastructure, e.g., variable dam operations, rainwater harvesting, is key. Scenario planning helps adapt policies to future extremes. Community engagement ensures relevance and equity in adaptation strategies. Ultimately, water management must embrace uncertainty, not resist it. Conclusion: the age of extremes. The world is entering an era where water extremes are the norm, not the exception. Responding effectively will require science, innovation, governance, and compassion. We must build systems that are anticipatory, inclusive, and regenerative, because the next flood or drought is not a matter of if, but when. Chapter 5: Water Security and Human Well-Being. To deny people water is to deny them life. Kofi Annan. Water security is more than just having enough water. It's about reliable access to safe water that supports health, sustains livelihoods, nourishes ecosystems, and enables development. It is a fundamental human right and a cornerstone of human well-being. In this chapter, we examine the critical links between water and the basic building blocks of life: health, food, energy, education, and dignity. We also look at how climate change is undermining water security in many parts of the world, and what it means for our shared future. What is water security? The United Nations defines water security as the capacity of a population to safeguard sustainable access to adequate quantities of acceptable quality water for sustaining livelihoods, human well-being, and socioeconomic development. Key elements of water security include: availability. Is there enough water? Access. Can people physically and economically obtain it? Quality. Is it safe and clean? Reliability. Is it available consistently over time? Resilience. Can systems withstand shocks like droughts or floods? When one or more of these dimensions fails, water insecurity results, with cascading consequences for people and societies. Water and public health. Water is central to health, not only for hydration but also for sanitation and disease prevention. Safe drinking water. Over 2 billion people globally lack safely managed drinking water services. Contaminated water spreads diseases like cholera, typhoid, hepatitis A, and diarrhea, which kills over 500,000 children annually. Sanitation and hygiene. Lack of sanitation affects over 3.6 billion people. Poor sanitation increases disease burden, especially in crowded urban or displaced settings. Women and girls suffer disproportionately, especially during menstruation and childbirth. Climate change worsens this through contaminated floodwaters, water shortages during drought, infrastructure damage during disasters, water and food security. Water and agriculture are inseparable. 70% of global freshwater withdrawals are used for irrigation. Rain-fed agriculture remains the dominant system in much of Africa and South Asia. Drought and crop failure. Climate-driven droughts and shifting rainfall patterns reduce crop yields and productivity. Force reliance on expensive irrigation or water trucking. Lead to food insecurity and malnutrition. Water-intensive foods. Some crops and livestock require massive water inputs. 1 kilogram of beef equals minus 15,000 liters of water. 1 kilogram of rice equals minus 2,500 liters. This raises questions about diet, equity, and sustainability in a water-stressed world. Water and livelihoods. Water supports industries, employment, and economic development. Fisheries and aquaculture depend on healthy rivers and lakes. Hydropower supports energy systems in over 150 countries. Tourism, especially in coastal or natural areas, is tied to water availability and quality. When water systems fail, entire economies can be disrupted. Farmers face bankruptcy during drought. Hydropower shortages lead to blackouts. Contaminated beaches or rivers affect tourism revenues. Water and education. The water crisis is also a crisis of opportunity, especially for women and children. Girls often drop out of school because they must fetch water or lack sanitation facilities. Time spent collecting water, up to 6 hours per day in some regions, means less time for school or work. Improving water access can transform communities. Every $1 invested in water and sanitation yields an estimated $4 in economic return. Water and gender equity. Water scarcity deepens existing gender inequalities. Women and girls are primarily responsible for water collection in 80% of households without on-site access. Lack of gender-sensitive sanitation impacts safety and dignity. Women's voices are often excluded from water management decisions. Empowering women in water governance improves outcomes across sectors, from conservation to conflict resolution. Urban water stress. By 2050, 2/3 of the global population will live in cities. Urban areas face unique water challenges. Aging infrastructure, such as leaking pipes and inadequate treatment systems. Growing demand that outpaces supply. Slums and informal settlements often lack safe water altogether. Climate change adds layers of complexity with more extreme rainfall causing flash floods, droughts reducing surface and groundwater supplies, sea level rise contaminating coastal aquifers. Cities like Cape Town, Sao Paulo, and Chennai have already faced near-total water shutdowns, a warning of what lies ahead without better planning. Conflict and displacement. Water scarcity and mismanagement can fuel local conflicts between farmers, herders, and urban users. Transboundary tensions in shared river basins, e.g. Nile, Jordan, Tigris, Euphrates. Mass displacement, as seen in regions like Lake Chad and the Syrian drought-affected areas. Water is increasingly recognized as a strategic security issue, requiring cooperation rather than competition. Climate justice and water equity. Climate impacts on water are not evenly distributed. Low-income and indigenous communities often face the highest risks with the fewest resources. Many who suffer most from water insecurity contribute least to climate change. Water justice involves fair access and representation in decision-making, recognition of traditional water knowledge, targeted support for the most vulnerable. Ensuring water security must be a core principle of climate justice. Building resilient water futures. Securing water for human well-being in a warming world requires sustainable infrastructure that is inclusive and climate adaptive. Integrated approaches that link water to health, food, energy, and ecosystems. Strong institutions and participatory governance. International cooperation, especially in shared watersheds. Water is life, but only if we manage it wisely, equitably, and with foresight. Chapter 6: Climate Change and Water Governance. Good water governance is not just about rules and institutions, it's about fairness, participation, and the courage to plan for uncertainty. Water governance lies at the heart of how societies respond to climate change. With rising scarcity, growing populations, and more frequent extremes, governance systems must evolve to ensure sustainable, equitable, and resilient water management. This chapter explores the key principles, challenges, and innovations in water governance in the context of a warming planet. What is water governance? Water governance refers to the political, institutional, and administrative frameworks through which decisions about water resources are made and implemented. Effective governance answers questions such as: who makes decisions about water? How are priorities set and enforced? What rules regulate use, pricing, and pollution? How are conflicts resolved and accountability ensured? It encompasses laws, regulations, rights, norms, and institutions, from national ministries to local water user associations. The climate challenge to governance. Climate change adds complexity to water governance. Uncertainty. Precipitation patterns are less predictable. Historical data is less reliable for future planning. Scale. Climate impacts cross administrative and national boundaries. Urgency. Decisions need to be made rapidly, often with incomplete information. Equity. Vulnerable groups may be marginalized in planning or disproportionately impacted. Climate-responsive governance requires flexibility, collaboration, and foresight, qualities not always built into traditional water systems. Principles of good water governance. To be effective under climate stress, water governance should be transparent, clear rules, data sharing, and accessible information. Inclusive, stakeholder participation, especially from marginalized groups. Accountable, clear responsibilities and mechanisms for oversight. Adaptive, ability to revise plans based on new knowledge or conditions. Equitable, fair distribution of costs, benefits, and risks. Integrated, linking water, land, energy, and environmental policies. These principles are widely endorsed, e.g. by the OECD, UN Water, but implementation remains uneven, especially in low-capacity settings. Institutional arrangements. Institutions play a critical role in how water is managed. National ministries oversee water policy, infrastructure, and regulation. River basin organizations manage water across watersheds, e.g. Mekong River Commission. Local governments deliver municipal services and enforce local bylaws. Water user associations, WUAs, represent farmers or communities in shared systems. Customary authorities play key roles in indigenous and rural contexts. Effective governance requires coordination across sectors and levels, often lacking in fragmented systems. Water rights and allocation. Water governance must determine who has the right to use water, and for what purposes. Models include riparian rights, based on land ownership, common and common law systems. Prior appropriation, first in time, first in right, used in the Western U.S. Public trust doctrine, water as a public good, Latin America, South Africa. Customary rights, local rules and traditions, prevalent in Africa and Asia. Climate change challenges these frameworks by reducing supply, increasing conflict, and exposing inequities in historical allocations. Transboundary water governance. More than 260 rivers cross international borders. Shared waters require cooperation rather than competition. Key mechanisms include treaties and conventions, e.g. UN Watercourses Convention. Joint commissions, e.g. Indus Waters Treaty, Nile Basin Initiative. Data sharing and conflict resolution platforms. Challenges in transboundary settings include power asymmetries, lack of trust, national security concerns. Climate change adds pressure by altering flows and increasing demand, making diplomacy and regional planning more important than ever. Urban water governance. Urban areas face a unique governance challenge. Multiple jurisdictions, cities, utilities, private actors. Informal settlements, often excluded from formal services. Public-private partnerships and privatization debates. Effective urban governance must strengthen public accountability. Invest in decentralized and inclusive systems. Regulate water quality and pricing fairly. Cities like Singapore, Bogotá, and Windhoek offer examples of integrated, climate-resilient urban water governance. Indigenous and customary governance. Indigenous communities often have long-standing systems for managing water, based on stewardship and reciprocity. Sacred relationships with water bodies. Customary rights and seasonal use patterns. Recognizing and integrating indigenous governance can improve sustainability, justice, and cultural preservation. However, many national laws fail to recognize these rights, creating conflict and marginalization. Climate adaptation and governance innovation. Adapting water governance for climate resilience involves scenario planning and decision-making under uncertainty, e.g., robust decision-making. Decentralization, giving power to local actors with context-specific knowledge. Adaptive licensing and permits that respond to changing conditions. Cross-sector coordination, linking water with energy, agriculture, and land use. Innovations like water funds, payment for ecosystem services, and smart water systems are being piloted in several regions. Toward just and climate-resilient governance. The future of water governance must be rooted in justice, flexibility, and cooperation. This includes empowering communities to participate in water decisions, sharing data and knowledge openly across sectors and borders, embedding climate risks into water planning, regulation, and finance, holding institutions accountable to serve both people and ecosystems. Water governance will determine whether societies adapt to climate stress or fracture under it. Strong, inclusive governance is our best defense against a future of water crisis. Chapter 7. Innovations in Water Management. Innovation is not just about new tools, it's about rethinking old systems with new purpose. The climate crisis demands not only better water management, but smarter water management. As traditional systems falter under the pressure of more extreme and unpredictable water conditions, innovation offers a path forward. From digital monitoring and precision irrigation to green infrastructure and desalination, technological and ecological innovations are helping communities around the world adapt to climate risks while securing water for future generations. The innovation imperative. Water innovation is essential for three main reasons. Efficiency, doing more with less water. Resilience, adapting systems to shocks and extremes. Sustainability, protecting water resources and ecosystems over time. Climate change alters the very nature of the water cycle. Innovation must not only react to change, it must anticipate and shape it. Smart water technologies. Digital technology is revolutionizing water management by improving monitoring, efficiency, and decision-making. Sensors and IoT, Internet of Things. Smart meters track water usage in real time. Leak detection sensors help reduce losses in urban water systems. Soil moisture probes allow precision irrigation on farms. These tools save water, reduce energy use, and improve transparency. Remote sensing and satellite monitoring. Used to monitor drought conditions, reservoir levels, and river flows. NASA's GRACE mission has revealed large-scale groundwater depletion. Satellites can also detect illegal water use and pollution plumes. Artificial intelligence and big data. Predictive models for flood forecasting and drought planning. AI systems can optimize dam operations or detect anomalies in water networks. Climate-informed decision support tools are helping policymakers manage risk. Agricultural innovations. Agriculture is the largest consumer of freshwater globally, making it a critical area for water innovation. Precision irrigation. Drip irrigation delivers water directly to plant roots with minimal waste. Automated irrigation systems respond to real-time soil and weather data. Variable rate irrigation, VRI, adjusts water delivery across different field zones. Drought-resilient crops. Genetic advances have produced drought-tolerant maize, rice, and wheat. Traditional knowledge also preserves indigenous crops that require less water. Crop diversification helps build climate-resilient farming systems. Agroecology and regenerative practices. Cover cropping, no-till farming, and mulching improve soil moisture retention. Agroforestry integrates trees into farming systems, enhancing water cycling. These methods offer both adaptation and mitigation benefits. Urban water innovations. Cities are adopting new models to tackle water scarcity, flooding, and pollution. Water recycling and reuse. Greywater systems recycle water from sinks, showers, and washing machines. Wastewater treatment plants now produce drinking quality water, e.g., Singapore's NE-water. Industrial reuse reduces freshwater demand in factories and power plants. Green infrastructure. Nature-based urban design solutions include rain gardens, green roofs, and bioswales to manage stormwater. Permeable pavements reduce runoff and recharge groundwater. Urban wetlands purify water and provide habitat. These solutions reduce flooding, cool cities, and restore ecosystems. Decentralized systems. In many growing cities, centralized infrastructure is failing or unaffordable. Innovation is shifting toward community-scale treatment systems, point-of-use purification technologies, e.g., household filters, mobile water ATMs, and pay-as-you-go services. These provide flexible, accessible solutions where government capacity is limited. Desalination and non-traditional sources. As freshwater sources dwindle, new supply options are emerging. Desalination converts seawater or brackish groundwater into potable water. Over 21,000 desalination plants now serve over 300 million people worldwide. Innovations like reverse osmosis membranes and solar-powered desalination are improving efficiency. Challenges include high energy use, unless powered by renewables. Cost. Disposal of salty brine waste. Atmospheric water harvesting. Technologies extract water from humidity or fog, useful in arid regions. Still expensive and small scale, but promising in remote or disaster-prone areas. Rainwater harvesting. Ancient practice now enhanced with modern storage and filtration systems. Crucial for off-grid homes, schools, and health centers in rural and peri-urban areas. Ecosystem-based approaches. Nature is one of the most powerful allies in water management. Watershed restoration. Reforestation and soil conservation improve water retention and reduce erosion. Beaver reintroduction in the US and UK has helped restore wetlands and regulate flows. Catchment management aligns land use with hydrology for long-term resilience. Wetlands protection. Wetlands store floodwaters, recharge aquifers, and filter pollutants. Over 60% of the world's wetlands have been lost, making protection urgent. Payment for ecosystem services, PES. Upstream landowners are paid to manage land in ways that benefit downstream users. Used in Latin America, East Africa, and parts of Asia. Strengthens the link between conservation and livelihoods. Innovation ecosystems and enablers. Technological breakthroughs don't happen in isolation. They need supportive ecosystems. Funding and incentives, e.g., green bonds, water innovation funds. Public-private partnerships. Knowledge-sharing platforms, e.g., UN Water, Water Action Hub. Inclusive design that works for the most vulnerable, not just the wealthy. Governments, NGOs, startups, and communities all have a role in scaling innovation. Barriers to innovation. Despite the promise, many innovations struggle to scale due to high upfront costs or lack of access to financing, institutional resistance or outdated regulations, lack of technical capacity or maintenance support, equity concerns, especially when innovations bypass low-income communities. Innovation must be context-sensitive, affordable, and inclusive to succeed broadly. Innovation for climate resilience. Ultimately, innovation in water is not just about solving today's problems, it's about building resilience for tomorrow. Effective innovation should reduce vulnerability to climate extremes, strengthen local capacity, be replicable and scalable, align with ecological sustainability. It's not the fanciest solution that wins, but the one that works best where it's needed most. Conclusion: rethinking what's possible. Water innovation represents hope. It offers tools to cope with change, restore balance, and reimagine how we relate to water and nature. But it must be guided by justice, sustainability, and humility, because innovation alone is not enough. The real transformation comes when technology, policy, and people move together toward a more resilient future. Chapter 8: Financing Water in a Changing Climate. Water may be free in nature, but delivering it safely, sustainably, and equitably requires smart investment. Despite its fundamental role in health, agriculture, energy, and climate resilience, water remains chronically underfunded. Climate change is making this shortfall more dangerous. Rising droughts, floods, and aging infrastructure require massive investment in resilient water systems. This chapter examines the financial dimensions of water management in a changing climate, how money flows, where gaps exist, and what innovative tools are helping close them. The global water finance gap. Estimates suggest that the world needs to invest over $1.7 trillion by 2030 in water infrastructure to meet basic needs and climate goals. Yet, public investment is insufficient and declining in many countries. Private investment is limited by low returns and high risks. Climate finance still prioritizes energy and carbon reduction over water adaptation. Water suffers from what some call the silent crisis of neglect, largely invisible until it becomes a disaster. Categories of water investment. Water-related investments fall into several categories. Basic services: pipes, pumps, treatment plants, and sanitation systems. Irrigation and storage: canals, dams, reservoirs, and drip systems. Natural infrastructure: wetland restoration, reforestation, aquifer recharge. Risk management: flood protection, drought mitigation, early warning systems. Digital infrastructure: smart meters, remote sensing, AI-based management. Each type of investment has its own risk profile, return expectation, and financing needs. Sources of water finance. Public financing. Governments remain the largest source of water investment. Finance through tax revenues, subsidies, or public debt. Challenges: fiscal constraints, corruption, political short-termism. User fees and tariffs. Revenue from household and industrial water users funds operations. Many utilities suffer from low-cost recovery and affordability challenges. Tiered pricing: lifeline tariffs and subsidies can balance access with financial viability. Private sector investment includes direct investment, public-private partnerships (PPPs), and service contracts. Often focused on urban or industrial projects with clear revenue streams. Requires stable regulation and low political risk to be attractive. International aid and development banks. Institutions like the World Bank, Asian Development Bank, and African Development Bank finance large-scale projects. Aid agencies fund smaller-scale and humanitarian initiatives. Blended finance models combine concessional loans with market-rate funding. Climate finance and water. Climate finance refers to funding for adaptation and mitigation projects. However, only about 3 to 5% of climate finance currently goes to water-related adaptation. Adaptation projects are harder to quantify in terms of ROI. Developing countries often face capacity barriers to accessing funds. Opportunities include Green Climate Fund, GCF, Adaptation Fund, NDC-linked water strategies under the Paris Agreement. Aligning water projects with climate adaptation goals increases their chances of financing. Innovative financing mechanisms. To bridge the funding gap, new tools and models are emerging. Blended finance combines public, philanthropic, and private capital to de-risk projects. Useful for climate-resilient infrastructure and innovation pilots. Examples: Kenya's Water Credit Program, Water.org's microloans. Green bonds and blue bonds. Green bonds finance environmentally sustainable projects. Blue bonds, a newer concept, target water and ocean-related investments. Seychelles issued the first sovereign blue bond in 2018 for marine conservation and fisheries. Insurance and risk transfer. Index-based insurance for droughts and floods is expanding. Sovereign disaster insurance, e.g., African risk capacity, helps countries respond to water shocks. Insurance incentivizes risk reduction measures and provides recovery funding. 8 water funds. Pool money from cities, utilities, and donors to invest in upstream watershed protection. Example, Fondo de Agua programs in Latin America. Deliver co-benefits like biodiversity conservation and carbon sequestration. Financing nature-based solutions. Investments in green infrastructure often struggle to compete with concrete-heavy, gray projects due to valuation challenges, how to price ecosystem benefits, longer timeframes to deliver returns, lack of institutional familiarity. However, tools like ecosystem service markets, carbon credits, and conservation finance are improving the business case. Barriers to effective financing. Common challenges include fragmented institutions and poor coordination, lack of bankable projects due to weak planning or unclear returns, creditworthiness issues of utilities and municipalities, equity gaps where low-income areas are least able to pay or attract investment. Financing systems must be restructured to serve both resilience and inclusion. Toward equitable and resilient financing. A climate-smart water finance system must prioritize adaptation in climate funding portfolios, include underserved communities and rural areas, leverage private capital without compromising equity or access, reward preventive action, not just post-disaster recovery, support long-term maintenance, not just construction. Ultimately, financing water is about investing in security, dignity, and resilience. Case studies. Case Study 1. Mexico City's water tariff reform. Introduced progressive pricing to fund infrastructure while ensuring affordability. Revenues reinvested into leak repairs and stormwater systems. Helped reduce consumption and increase cost recovery. Case Study 2. South Africa's Climate Adaptation Finance Facility. Offered low-interest loans to farmers for water-saving tech and crop diversification. Supported by the GCF and local banks. Blended finance unlocked adaptation investments in vulnerable regions. Case Study 3. Netherlands Delta Fund. Long-term fund for climate-resilient water infrastructure. Financed through annual tax contributions and public debt. Combines gray and green infrastructure with community engagement. Conclusion: money meets mission. Financing water in a warming world requires more than capital. It demands courageous policy, smart design, and global solidarity. As risks grow and needs mount, the choice is clear. Invest in water resilience today or pay a much higher price tomorrow. Chapter 9. Education, Engagement, and Behavior Change. The biggest change is not in the pipes or the policies, it's in how we think about and use water. When it comes to tackling the water crisis, technology and policy are essential, but lasting solutions lie in the behavioral changes of individuals, communities, and organizations. Changing how we view and use water, moving from a mindset of waste to one of stewardship, can have a profound impact. This chapter explores the power of education, engagement, and behavior change in creating a water-wise future that is resilient to the impacts of climate change. The power of education in water management. Education is the foundation upon which awareness, understanding, and action are built. It empowers individuals, communities, and leaders to make informed decisions that benefit both the environment and society. Formal education. Curricula that integrate climate change and water issues are vital. Schools and universities can equip the next generation with the knowledge to build more resilient systems. Programs like water science, environmental studies, and sustainability courses are growing in importance. Universities and technical institutions train the water professionals of tomorrow, including engineers, planners, and policymakers. Community-based education. In rural and marginalized areas, community education programs provide hands-on training in water conservation, rainwater harvesting, and sustainable farming techniques. Indigenous knowledge plays a crucial role in educating communities about local water management practices that have been honed over generations. Local radio programs, workshops, and field schools can engage community members, especially women and children, who are often the primary managers of water in households. Public awareness campaigns. Media, social media, and documentaries raise awareness about the importance of water and the challenges posed by climate change. Governments and NGOs use public service announcements to encourage water-saving behaviors, like reducing water wastage and fixing leaks. Campaigns like the Water Conservation Challenge or World Water Day help bring water issues into the global conversation. The role of engagement in water stewardship. Engagement goes beyond education. It involves fostering a sense of ownership and responsibility for water resources. Stakeholder engagement in water management. Inclusive decision-making ensures that all relevant stakeholders, including local communities, indigenous groups, businesses, and government agencies, are involved in water governance. Successful engagement requires listening, respect for different knowledge systems, and incorporating diverse perspectives into planning and decision-making. Collaborative models, such as multi-stakeholder platforms and community-driven water projects, lead to more effective and sustainable solutions. Public-private partnerships, PPPs. PPPs can mobilize the resources and expertise needed to tackle complex water challenges, such as building water infrastructure in urban areas or supporting water efficiency in industries. The private sector's role includes investing in innovative water technologies and corporate social responsibility initiatives focused on water stewardship. Businesses can also help through water stewardship programs, where they work alongside local communities to manage water resources responsibly. Engaging youth and schools. Youth engagement is key to shaping the future of water management. Schools and youth groups often lead grassroots efforts in water conservation and environmental activism. Programs like Water Warriors encourage children to take water conservation initiatives to their schools and homes. Youth organizations and student unions can advocate for better water policies at local, national, and global levels. Behavioral change for water conservation. The water crisis cannot be solved by technology alone. Behavioral changes at all levels, individual, household, and industrial, are essential for long-term sustainability. Household-level behavior change. Reducing water consumption through simple changes, turning off taps, using low-flow showerheads, fixing leaks, and washing clothes in full loads. Rainwater harvesting and greywater reuse can reduce dependency on municipal water systems, especially in drought-prone regions. Awareness of water footprints. Understanding the hidden water used in products such as food, e.g., the water required to grow a hamburger, can encourage more conscious consumption. Industrial and agricultural behavior change. Precision agriculture. Using technology to minimize water use in farming, e.g., drip irrigation, soil moisture sensors. Industry adoption of water efficiency measures. Encouraging industries to adopt practices such as closed-loop water systems or zero water discharge. Water use reduction in manufacturing. Many industries are starting to monitor and reduce their water footprints, using less water in the production process and recycling water on-site. Encouraging government and institutional accountability. Government and institutional transparency. Citizen engagement in monitoring and ensuring that water policies and laws are effectively enforced. Regulations. Implementing water-efficient standards in construction, urban planning, and energy generation. Incentives for water-saving technologies. Government incentives or subsidies for adopting water-efficient appliances and systems in households and industries. Tools for promoting behavior change. Behavioral change requires a combination of education, incentives, regulations, and community engagement. Economic incentives. Water pricing. Appropriate pricing structures can encourage water conservation by reflecting the true cost of water. Subsidies for water-saving technologies. Government subsidies for water-efficient appliances, irrigation systems, and industrial upgrades can speed the adoption of best practices. Cash for conservation. Rewarding households or businesses for reduced water consumption with rebates, tax breaks, or direct cash payments. Social norms and peer pressure. Peer influence can be a powerful tool. Local communities often adopt new behaviors when they see their neighbors doing the same. Community-based campaigns encourage residents to take collective action, such as adopting water-saving habits or organizing cleanup and water conservation efforts. Public recognition programs for businesses and households that excel in water conservation can help spread the culture of stewardship. Behavioral nudges. Water-saving tips on utility bills, including simple messages about water-saving practices on utility bills, can remind people to reduce consumption. Smart meters and apps. Digital tools that show real-time water consumption can encourage users to change their behavior by showing how much water they are using. Education through visuals and media. Infographics and social media campaigns visually demonstrate the importance of water conservation and the impact of individual actions. Documentaries and public service announcements can create emotional connections to the cause, illustrating the human and environmental cost of water scarcity. Overcoming challenges to behavior change. Achieving behavior change is not easy. Some of the barriers include habitual behavior. People are often reluctant to change routines, such as taking longer showers or leaving the tap running while brushing their teeth. Perceived cost. People may resist investing in water-efficient technologies due to upfront costs, even if the long-term savings are greater. Lack of immediate benefits. Water conservation may seem abstract or distant, especially in areas where water seems abundant. To overcome these barriers, solutions must be cost-effective, visible, and aligned with people's values and daily routines. The role of policy in behavioral change. Governments play a key role in shaping behaviors through regulations and standards that incentivize water-efficient products and services. Public education campaigns that raise awareness about the value of water. Legislation that mandates water conservation in agriculture, industry, and urban areas. For policies to be effective, they must be well-designed and properly enforced, while also ensuring that vulnerable groups are not disproportionately affected. Conclusion: a collective effort. Water management is not just about technology or policy, it's about changing the way we think about water and our relationship with it. Education, engagement, and behavior change are powerful tools in making water conservation a global norm. Every individual, community, and institution has a role to play in this transformation. Chapter 10: The Future of Water Management. The future of water management is not just about surviving the climate crisis, it's about thriving in a new era of collaboration, innovation, and sustainability. The world is facing an unprecedented challenge, balancing the growing demand for water with the stresses imposed by climate change. As the 21st century unfolds, water management is at a crossroads, driven by the twin forces of innovation and crisis management. The decisions we make today will define the water security of tomorrow. This chapter explores emerging trends, technologies, and governance models that will shape the future of water management, equipping us with the tools we need to create a resilient, equitable, and sustainable water future. Emerging trends in water management. The rise of smart water systems. Smart water management refers to the integration of digital technologies and data analytics to improve the efficiency and resilience of water systems. With the advent of the Internet of Things, IoT, artificial intelligence, AI, and big data, Water utilities and managers can optimize operations, predict demands, and reduce waste. Smart meters will help consumers monitor their water usage in real time, fostering behavioral changes in water conservation. AI-powered algorithms will predict flood risks and water quality changes, improving disaster response and infrastructure planning. Sensors and IoT devices will provide granular real-time data on water quality, supply levels, and system health, allowing for more effective maintenance and quicker responses to leaks, contamination, and other challenges. Decentralization of water systems. As traditional, centralized water management systems face increased pressure from climate change, urbanization, and aging infrastructure, a shift toward decentralized water systems is emerging. This trend is powered by advances in modular technologies that provide more flexible, scalable solutions. Rainwater harvesting systems, small-scale desalination units, and on-site wastewater treatment can ensure local communities have access to water, regardless of central supply disruptions. The decentralization trend allows for more community-driven decision-making, where local knowledge and needs shape water management solutions. Microgrids for water systems are becoming a viable option in regions where centralized infrastructure is either unavailable or too expensive. Water-energy nexus. The water-energy nexus, the relationship between water use and energy production, is becoming increasingly important as we transition to renewable energy sources and face challenges of water scarcity. Energy production, especially through hydropower and thermoelectric power, relies heavily on water resources, while energy-intensive processes like desalination exacerbate water consumption. Future water management will require integrated planning that aligns energy production, water use, and climate goals to minimize inefficiencies and maximize synergies. Energy-efficient water technologies, such as low-energy desalination or solar-powered water pumps, will reduce both water consumption and carbon emissions. Circular water systems that combine energy recovery from wastewater will help reduce pressure on both water and energy resources. Key technologies shaping the future. Advanced water treatment technologies. Innovative water treatment solutions are evolving to meet the demands of a changing climate and growing populations. Membrane filtration technologies like reverse osmosis will continue to advance, improving the efficiency of desalination and wastewater treatment processes. Electrochemical treatment and biological filtration processes offer more sustainable, cost-effective ways of purifying water. Nanotechnology and graphene filters promise to revolutionize filtration, allowing for the removal of contaminants at a molecular level with fewer chemicals and less energy. Desalination 2.0. As freshwater resources become scarcer and the demand for clean water grows, desalination will play an increasingly vital role in meeting global water needs. Solar desalination and wave-powered desalination systems are on the rise, making the process more energy efficient and environmentally friendly. Zero liquid discharge (ZLD) systems will be implemented to reduce the harmful environmental impact of brine disposal, a common issue with traditional desalination plants. Energy recovery devices in desalination plants will improve efficiency, helping to bring down the overall cost of desalinated water. Climate-smart agriculture. Agriculture is one of the largest consumers of water, and as the planet warms, the need for climate-smart agricultural practices is more pressing than ever. Precision irrigation systems that monitor soil moisture, crop water needs, and weather patterns will allow farmers to use water more efficiently. Drought-resistant crops and smart crop rotation systems will be developed to minimize water usage while maintaining food security. Vertical farming and hydroponics offer innovative ways to grow food with significantly less water, using closed-loop systems where water is recycled rather than discarded. The future of water governance. As the climate crisis deepens, new governance models will be needed to manage the growing complexity of water management. Collaborative governance will be essential for ensuring that water is managed effectively, equitably, and sustainably. Integrated Water Resources Management, IWRM. The future of water management will focus on integrated, basin-wide management of water resources. IWRM promotes collaboration across sectors, communities, and administrative boundaries to address water-related challenges at the regional and local levels. IWRM will become the standard for addressing water shortages, pollution, and ecosystem health in a coordinated manner. Governments, the private sector, and civil society will need to work together to ensure that water policies are inclusive and meet the needs of both people and nature. Water equity and justice. The future of water management must prioritize equity and justice, ensuring that vulnerable communities are not left behind as the world adapts to climate change. Water rights will be a major issue in the coming decades, with many countries grappling with how to allocate scarce resources fairly. Water pricing will need to reflect the value of water, while ensuring that the poor and marginalized can still access it. Local-level governance and participatory decision-making will ensure that all stakeholders, especially indigenous peoples, women, and communities at risk, have a say in how water is managed. Global cooperation. Water is a global resource, and the future will see increased collaboration across borders. Many of the world's largest rivers, such as the Nile, Mekong, and Amazon, are shared by multiple countries, and disputes over water rights are growing. Transboundary water management agreements will be essential for resolving conflicts and ensuring equitable access to shared water resources. International water diplomacy will become a crucial aspect of global climate negotiations, with water scarcity and distribution playing a central role in future peace and security concerns. The role of public and private sectors in shaping the future. Public sector leadership. Governments will play a critical role in setting the regulatory frameworks for water management, investing in resilient infrastructure, and ensuring that water governance is transparent and accountable. Public leadership will be essential in building resilient water infrastructure that can withstand the impacts of climate change, ensuring equitable access to water, especially for underserved populations, integrating water management into broader climate adaptation and mitigation strategies. Private sector innovation. The private sector will continue to drive technological innovation and investment in water management solutions. Corporate responsibility, especially in industries with high water footprints, will help reduce water stress. Private actors can develop water-efficient technologies for agriculture, industry, and urban systems. Invest in water stewardship programs that promote conservation and sustainable use. Engage in partnerships with governments and NGOs to address local water challenges. Conclusion: water's crucial role in the future. Water is the lifeblood of our planet. Without it, nothing thrives. As we navigate the complex realities of a changing climate, the future of water management will require bold thinking, innovative solutions, and collaborative action. The future of water management is not one of scarcity and conflict, but of opportunity and cooperation. It is a future in which technology, governance, and human ingenuity combine to ensure that water remains a resource for all, now and in the years to come. Chapter 11. Case Studies in Water Management. In the face of water scarcity and climate change, real-world solutions can offer a blueprint for a sustainable future. While the challenges of water management are global, the solutions are often found in local action and innovative approaches that can be scaled and adapted. In this chapter, we examine several case studies from around the world that highlight both the struggles and successes in managing water resources under changing climate conditions. These stories provide valuable lessons on how technology, policy, collaboration, and community engagement can work together to achieve more sustainable and resilient water systems. Case Study 1. The Netherlands, Water Management Through Innovation. The Netherlands, a country that is more than 1/4 below sea level, is a global leader in water management. It has long been at the forefront of tackling challenges related to water scarcity, floods, and rising sea levels. Strategies and solutions. Delta Works. This is one of the largest and most sophisticated systems of dams, sluices, locks, dikes, and storm surge barriers in the world. It was built to protect the Netherlands from flooding due to its low-lying geography and rising sea levels. Room for the River program. In response to flooding, the Dutch government has embraced a policy that allows rivers to flood in controlled designated areas rather than resisting flooding with dams alone. This approach, called living with water, encourages floodplains to store excess water and release it gradually. Lessons learned. Flexibility in water management, allowing for adaptive responses to changing conditions. The importance of collaboration between government agencies, engineers, and local communities in designing and implementing solutions. The value of innovative nature-based solutions, such as restoring wetlands, as part of flood control measures. Case Study 2, Singapore, a model of water resilience. Singapore is one of the few countries in the world to have made significant strides in water resilience despite its limited natural water resources. The island nation has been able to overcome water scarcity through innovation, technology, and strategic partnerships. Strategies and solutions. NE-Water. Singapore's NE-Water initiative involves the purification and recycling of wastewater to meet 40% of the country's water needs. This advanced membrane filtration and ultraviolet disinfection process has made Singapore a global leader in water reuse technology. Desalination. Singapore has invested in energy-efficient desalination plants that supply clean water from seawater, increasing the country's resilience to droughts and changes in rainfall patterns. Water conservation policies. Through education and public awareness, Singapore has also drastically reduced per capita water usage, promoting conservation in households and industries. Lessons learned. Innovation in water recycling and desalination can offer alternative sources of water in water-scarce regions. Strong governance and policy are key to ensuring that technological solutions, such as water reuse, are effective and safe. Public education and behavioral change are essential components in reducing water consumption and fostering a culture of conservation. Case Study 3, California, USA, addressing drought through policy and technology. California is one of the most water-stressed regions in the United States, facing persistent droughts exacerbated by climate change. However, it has also implemented groundbreaking water management strategies to ensure a sustainable water future. Strategies and solutions. Water market system. California has implemented a water trading system, which allows farmers and other users to buy and sell water rights. This flexible market-based solution has helped redistribute water to where it's needed most, particularly during dry years. Groundwater management. California's Sustainable Groundwater Management Act, SGMA, passed in 2014, has created a framework for managing groundwater use and preventing over-extraction, a key issue during droughts. Smart irrigation technologies. In agriculture, the state has adopted smart irrigation systems, including drip irrigation and soil moisture sensors, to minimize water waste while maximizing crop yield. Lessons learned. Policy frameworks that regulate groundwater use and incentivize water trading can help manage resources during times of drought. Water conservation technologies, such as drip irrigation and water-efficient crops, play a crucial role in maintaining agricultural productivity while reducing water use. Collaboration between state agencies, local governments, and farmers is essential in managing water resources effectively across diverse sectors. Case Study 4, Cape Town, South Africa, the Day Zero Crisis. Cape Town, a major city in South Africa, was on the brink of a Day Zero water crisis in 2018, when the city's reservoirs were predicted to run dry due to a severe drought exacerbated by climate change. The crisis led to an urgent rethinking of water management and policy. Strategies and solutions. Water rationing. In 2018, Cape Town introduced stringent water rationing measures, restricting household water use to 50 liters per person per day. The public was educated on water-saving measures, such as reducing shower time and limiting lawn watering. Water recycling. The city initiated projects to recycle wastewater, converting it into potable water for industrial use. Desalination. Cape Town has begun investing in small-scale desalination plants, with plans to expand its capacity as a long-term solution to drought. Lessons learned. Rapid action and effective communication are vital in managing acute water crises. Public engagement and education are critical in gaining public buy-in for water-saving measures. Diversification of water sources, including desalination, recycling, and stormwater harvesting, can help reduce dependency on traditional sources. Case Study 5. The Murray-Darling Basin, Australia, managing transboundary water resources. The Murray-Darling Basin is Australia's most significant river system, providing water for agricultural, industrial, and urban use across several states. The basin has been severely impacted by droughts, poor management, and climate change, leading to conflicts over water allocation and management. Strategies and solutions. Murray-Darling Basin Plan. The Australian government implemented the Murray-Darling Basin Plan, which seeks to allocate water equitably among farmers, communities, and the environment. This plan includes provisions for environmental flows to restore ecosystems and protect biodiversity. Water trading. A water trading market has been developed in the basin, allowing water users to trade water rights and efficiently allocate resources. Integrated management. The plan includes collaborative management across state boundaries, engaging stakeholders from all sectors to find sustainable solutions. Lessons learned. Transboundary management requires cooperation across state and national borders to ensure that all stakeholders have access to sufficient water resources. Environmental considerations, such as the need for water to sustain ecosystems, must be factored into water allocation plans. Market-based solutions, such as water trading, can provide flexibility and efficiency in resource allocation. Case Study 6. India's Water Crisis, Community-Led Solutions in Rajasthan. In the arid region of Rajasthan, India, water scarcity is a perennial issue due to low rainfall, high evaporation, and growing populations. However, local communities have adopted innovative solutions to manage their water resources. Strategies and solutions. Johad systems. Local communities in Rajasthan have traditionally relied on johads, small community-built check dams that capture rainwater, store it in ponds, and recharge groundwater. Rainwater harvesting. Rajasthan has implemented widespread rainwater harvesting systems at the household and community levels, allowing people to collect and store water during the monsoon season for use during dry periods. Sustainable agriculture. Local farmers have embraced water-efficient agricultural practices, including the use of xerophytic plants, plants adapted to dry climates, and techniques like mulching to retain soil moisture. Lessons learned. Community-driven solutions can be incredibly effective in regions where government infrastructure is lacking. Traditional knowledge, such as rainwater harvesting and local water conservation techniques, plays an important role in sustainable water management. Bottom-up approaches that involve local stakeholders in decision-making are more likely to succeed in ensuring long-term sustainability. Conclusion: Global lessons for a water-wise future. The case studies presented in this chapter demonstrate that while the challenges are immense, solutions do exist. From high-tech innovations to community-driven actions, the future of water management lies in diverse approaches that combine innovation, collaboration, and local knowledge. By learning from these examples and adapting them to our unique circumstances, we can build a water-wise future where water is used wisely, conserved, and shared equitably. Chapter 12. The role of policy and governance in shaping the future of water. Water governance is not just about managing a resource. It's about managing the lifeblood of human civilization itself. As the world faces unprecedented challenges due to climate change, the effective management of water resources has become a central issue for ensuring the future of our planet and its inhabitants. Water is not only a basic human need, but also a cornerstone of economic development, agriculture, health, and ecosystem services. This chapter explores the critical role that policy frameworks, governance structures, and international cooperation will play in shaping the way we manage water in a rapidly changing world. Whether at the local, national, or global level, effective water governance is key to ensuring that water is equitably distributed, sustainably managed, and resilient to the effects of climate change. The need for effective water governance. Understanding water governance. Water governance refers to the rules, institutions, and processes that guide how water resources are managed, allocated, and protected. It includes the roles and responsibilities of government agencies, private sector actors, civil society, and communities in decision-making processes related to water. Effective water governance is essential because water is finite and vulnerable. The increasing unpredictability of water availability due to climate change and population growth necessitates smart, adaptive governance systems. Water is essential for all sectors. From agriculture to industry to households, water impacts almost every aspect of modern life. Water-related conflicts. Poor governance can lead to competition and even conflict over water resources, especially in water-scarce regions or areas with shared water bodies. Principles of good water governance. For water governance to be effective, it must be based on key principles. Equity, ensuring that water is allocated fairly, especially to marginalized communities. Sustainability, ensuring that water resources are used in ways that maintain their availability for future generations. Transparency, decision-making must be open and accessible to all stakeholders, ensuring public trust. Accountability, water management authorities must be answerable to the public for their decisions and actions. Participation, including all stakeholders, especially local communities, in water governance decisions. The role of policy in water management. Water policies are central to how governments manage water resources. These policies provide the framework for regulation, allocation, and conservation of water, influencing how resources are distributed and utilized across sectors. National water policies. National water policies play an essential role in setting out the long-term vision and strategy for managing water resources. These policies must address water allocation, who gets water, how much they get, and under what conditions. Water quality and pollution control, ensuring that water resources are protected from contamination and are safe for human consumption. Water conservation and efficiency, encouraging the use of water-saving technologies and promoting behavior change to reduce waste. Climate adaptation, developing strategies to ensure water systems can adapt to changing climate patterns, such as increased droughts or floods. A strong national policy provides the legal and regulatory framework needed to manage water effectively, but it must be flexible enough to adapt to evolving environmental and social challenges. The role of local and regional policies. Local and regional policies are just as crucial in the context of water management, as they take into account the unique needs of specific communities, ecosystems, and water systems. These policies can address local water quality management, such as pollution reduction and improving sanitation systems. Decentralized water systems that empower local governments and communities to manage their own water resources. Coastal zone management, which involves managing water resources and ecosystems in areas vulnerable to sea level rise and storm surges. Integrated water resources management, IWRM. A key concept in modern water governance is integrated water resources management, IWRM. IWRM is a holistic cross-sectoral approach to managing water resources that takes into account the interconnections between water quality, water quantity, ecosystems, and human development. Key components of IWRM. IWRM emphasizes the following key components. Water management at the river basin scale. Recognizing that water systems are interconnected, IWRM promotes managing water resources on a basin-wide scale rather than within political boundaries. Cross-sectoral coordination. IWRM involves coordination between sectors such as agriculture, energy, industry, and urban development to ensure sustainable and equitable water use. Community participation. IWRM emphasizes involving local communities in the management of water resources, recognizing that local knowledge and engagement are essential for effective governance. Implementing IWRM. To implement IWRM effectively, there needs to be strong institutions that can manage water resources at different scales, legal frameworks that allow for coordination across sectors and scales, stakeholder engagement to ensure that all relevant parties, including marginalized groups, have a voice in decision-making, international water law, and transboundary water governance. As the world's freshwater resources are shared across borders, transboundary water governance becomes increasingly important. Over 300 transboundary rivers cross international borders, and disagreements over water distribution have led to tensions and conflicts. International water law. International water law is designed to regulate how countries share and manage transboundary water resources. The United Nations Watercourses Convention, adopted in 1997, is a key framework for promoting cooperation among nations sharing freshwater resources. Key principles of international water law include equitable and reasonable utilization. Each country sharing a water resource has a right to use it, but that use must be equitable and based on reasonable principles. No harm. Countries are obligated not to cause harm to other countries that share a watercourse, ensuring that activities in one country do not damage the water quality or availability for others. Cooperation. Countries must cooperate in managing shared water resources and may be required to consult on projects that could impact the shared resource. Examples of transboundary water cooperation. The Nile Basin Initiative. Countries along the Nile River have worked together to manage the river's resources through the Nile Basin Initiative, focusing on joint development and equitable distribution. The Indus Water Treaty. Signed between India and Pakistan in 1960, this treaty has successfully resolved disputes over the waters of the Indus River and its tributaries, providing a framework for conflict resolution. The Mekong River Commission, a regional body that manages the Mekong River, involving Cambodia, Laos, Thailand, and Vietnam, with a focus on sustainable development and cooperation in the face of climate change. Climate change, water governance, and policy integration. As the impacts of climate change continue to intensify, water governance and policies must be climate-sensitive and adaptive to ensure resilience in water management systems. This requires integrating water management into climate policies, ensuring that water considerations are included in national and international climate adaptation and mitigation plans. Investing in climate-resilient infrastructure. This includes building dams, levees, and water treatment plants that can withstand extreme weather events like floods, droughts, and heat waves. Monitoring and forecasting. Using data and modeling tools to predict the impacts of climate change on water resources, helping to make informed decisions on resource allocation and infrastructure development. The role of the private sector and civil society. While governments play a central role in water governance, the private sector and civil society also have crucial roles to play. Private sector. Businesses involved in industries like agriculture, energy, and manufacturing have significant water footprints. They must adopt water-efficient technologies and practices to minimize their impact on local and global water resources. Civil society. Local communities, NGOs, and activists play a vital role in advocating for water justice, community participation, and transparency in decision-making. They can hold governments and corporations accountable for their actions and ensure that water policies are inclusive and equitable. Conclusion: charting a path toward sustainable water governance. Effective water governance is essential for securing a sustainable water future. Through strong policies, integrated management, and international cooperation, we can address the challenges of water scarcity, pollution, and climate change. Governments, the private sector, and civil society must work together to ensure that water remains a resource for all, protecting both human and ecological needs. As we look to the future, it is clear that water governance must evolve to meet the complexities of a changing climate. This requires new approaches, innovative solutions, and a commitment to equity and sustainability. Chapter 13: The Role of Education and Advocacy in Water Conservation. Water conservation begins with awareness. When people understand the value of water, they will act to protect it. Water scarcity, pollution, and climate change have made water conservation more urgent than ever. However, effective water management cannot be achieved solely through technological innovations, infrastructure development, and policies. It requires a collective shift in how we view, use, and protect water, one that begins with education and advocacy. In this chapter, we explore how education, public awareness campaigns, and advocacy can inspire individual actions, policy changes, and community engagement in the fight for sustainable water management. The power of education in water conservation. Education serves as the foundation for fostering a culture of water conservation. It empowers individuals, communities, and organizations to understand the importance of water and adopt behaviors that ensure its sustainable use. Formal education, teaching water management in schools. Formal education plays a key role in shaping attitudes toward water conservation, starting from an early age. Integrating water management topics into school curricula helps children understand the significance of water as a limited resource. Some initiatives include environmental education programs, teaching students about the water cycle, climate change impacts on water systems, and the importance of water conservation. Water science clubs, encouraging students to explore innovative solutions for water-saving technologies, such as rainwater harvesting and water-efficient irrigation methods. Water conservation challenges. Schools can create challenges where students participate in water-saving campaigns or implement water-efficient practices at home. By making water education a part of the formal curriculum, we can shape future generations to become stewards of water resources, instilling a deep sense of responsibility toward preserving water. Community education, reaching people where they live. While formal education is essential, community education has the potential to reach a broader and more diverse audience. This involves raising awareness, sharing knowledge, and engaging people in practical water-saving activities. Some strategies include workshops and seminars. Local governments and NGOs can host workshops that teach people how to reduce water consumption, fix leaks, and implement rainwater harvesting techniques. Public service announcements. Using mass media channels like television, radio, and social media to communicate the importance of water conservation and share tips on saving water. Water-saving toolkits, distributing free or low-cost toolkits containing water-saving devices such as low-flow showerheads, faucet aerators, and leak detection tablets. By connecting with communities on a personal level, education campaigns can spark lasting behavioral changes and create a sense of urgency around water conservation. The role of advocacy in water conservation. Advocacy is the process of influencing decision-makers to prioritize water issues, drive change, and secure funding for water conservation initiatives. It is essential to create a public demand for action that leads to policies, regulations, and investments aimed at improving water management. Grassroots advocacy, Empowering local communities. Local communities are often the first to feel the effects of water scarcity and pollution, and they are well positioned to advocate for solutions. Grassroots advocacy involves community-led campaigns, empowering local people to take action, such as organizing local cleanups, advocating for better water infrastructure, or lobbying for changes to local water policies. Water user groups. Communities that depend on shared water resources, like rivers or lakes, can form water user associations to collectively manage their water supplies and advocate for fair and sustainable use. Collaboration with NGOs. Non-governmental organizations can provide the resources, knowledge, and platform needed for local advocacy, helping communities organize campaigns that raise awareness about local water challenges. Grassroots advocacy is crucial for raising the voices of those who may not have access to decision-makers, allowing them to advocate for their water needs and solutions. Policy advocacy, shaping national and global water policies. While local advocacy is important, policy advocacy at the national and international levels is key to driving systemic changes in water management. Some strategies include lobbying for water-focused legislation, advocating for the creation or strengthening of water laws, such as laws for water rights, water pricing, and pollution control. Collaborating with international organizations. NGOs and advocacy groups can collaborate with international bodies like the United Nations and the World Bank to advocate for global water policies that address issues like water access, sanitation, and climate adaptation. Engaging with policymakers. Advocacy organizations can work closely with legislators to ensure that water issues are incorporated into national climate action plans, agricultural policies, and urban development strategies. Through advocacy, civil society can hold governments accountable and demand policies that prioritize water sustainability and climate resilience. Public awareness campaigns, changing water use habits. Public awareness campaigns are powerful tools in changing individual behavior. They inform, inspire, and engage the public in taking concrete steps to conserve water. A few examples include global campaigns. World Water Day, March 22nd. This annual event organized by the United Nations is an opportunity to raise global awareness about water issues and inspire action. The theme of World Water Day shifts every year, focusing on specific aspects of water sustainability, such as water access, sanitation, or conservation. The Save Water campaigns. Global brands and environmental organizations often run campaigns encouraging people to reduce water use in their daily lives. Campaigns like Every Drop Counts or Save Water, Secure the Future emphasize the importance of simple water-saving habits, such as turning off the tap while brushing teeth, fixing leaks, and using water-efficient appliances. Local and regional campaigns. Water-wise cities. Some cities have launched campaigns encouraging residents to implement water-saving technologies, such as installing rainwater harvesting systems or converting lawns to drought-tolerant gardens. Water conservation challenges. Local governments and NGOs may create friendly competitions that challenge households to reduce their water usage, offering prizes for those who save the most water or adopt the most effective water conservation methods. Public awareness campaigns create a sense of shared responsibility, helping individuals realize that their small actions, when multiplied across a community, can make a huge difference. The role of technology in education and advocacy. Technology can significantly enhance education and advocacy efforts by increasing accessibility and engagement. Here's how. Digital platforms for water education. Mobile apps. Many apps provide users with tools to track water usage and offer tips for saving water, such as Drop Country or WaterSmart. Webinars and online courses. Educational organizations and universities are offering free online courses on water management, water conservation techniques, and climate change adaptation. These can be accessed by anyone, anywhere, making education about water resources more widely available. Social media. Platforms like Instagram, Twitter, and YouTube allow environmental activists to spread the word about water conservation, share educational content, and mobilize communities for action. Smart technologies for advocacy. Water sensors and smart meters. Technologies that measure water usage in real time allow individuals and organizations to monitor and adjust their water consumption. Data visualization tools. Interactive maps and charts can help visualize water scarcity, pollution levels, and water distribution, empowering advocates with the data needed to push for change. Technology amplifies the impact of education and advocacy efforts, creating new opportunities for engagement, collaboration, and action. Water conservation as a collective effort. While individual action is crucial, solving the global water crisis requires collective action from governments, businesses, communities, and individuals. Education and advocacy play a critical role in creating a broad-based movement for change. By empowering people with knowledge and giving them the tools to act, we can shift our collective behavior toward sustainable water use. As we work to raise awareness and inspire action, it's important to remember that water conservation is not just a personal responsibility, but a shared global challenge. Through collaboration, advocacy, and education, we can ensure that water remains a resource that sustains life for generations to come. Chapter 14: Future Innovations in Water Technology. The future of water is not just about preserving what we have, it's about innovating to ensure that we meet the demands of tomorrow. As the world grapples with climate change, population growth, and rising water demand, technological innovation has the potential to reshape how we manage one of our most vital resources, water. From smart irrigation systems to advanced desalination technologies, the future of water management lies in innovation, adaptation, and sustainability. This chapter explores the emerging technologies and innovative solutions that could help us tackle the challenges of water scarcity, contamination, and inefficiency in the coming decades. The promise of desalination, turning saltwater into freshwater. Desalination, the process of removing salt and other impurities from seawater, has long been seen as a potential solution to freshwater scarcity, especially in regions where natural freshwater sources are limited. While desalination is already being used in several parts of the world, such as the Middle East and California, ongoing innovations are making this technology more efficient, cost-effective, and environmentally friendly. Advances in reverse osmosis. Reverse osmosis, RO, is the most common method of desalination, where water is forced through a semi-permeable membrane to remove salt and other impurities. While this process is energy-intensive, recent innovations in membrane technology are improving efficiency. Graphene-based membranes. Graphene, a one-atom-thick layer of carbon atoms, has been found to be a highly effective material for filtering salts and impurities. Researchers are exploring the use of graphene oxide membranes to increase the speed and efficiency of the desalination process while reducing energy consumption. Pressure-retarded osmosis. PRO is a process that uses the osmotic pressure difference between freshwater and seawater to generate energy, which can then be used to power the desalination process. This technology has the potential to make desalination a more sustainable and energy-efficient option. Solar desalination. Solar desalination is an emerging innovation that uses solar energy to power desalination processes. The solar still and solar desalination plants utilize the sun's heat to evaporate seawater and then condense the vapor into fresh water. Some notable developments include solar desalination farms. Large-scale solar desalination farms using concentrated solar power, CSP, or photovoltaic panels can produce large quantities of fresh water, particularly in sun-rich regions like the Middle East and Africa. Solar stills. Small-scale solar stills are being used in remote communities where energy resources are scarce, offering a simple and low-cost solution to provide fresh drinking water. Smart irrigation. Watering plants with precision. Agriculture is one of the largest consumers of freshwater, accounting for approximately 70% of global water use. Traditional irrigation methods, such as flood irrigation, are inefficient, often leading to water waste and soil degradation. Smart irrigation technologies aim to address these inefficiencies by using data, sensors, and automation to deliver water more efficiently to crops. Internet of Things, IoT in agriculture. The Internet of Things, IoT, is revolutionizing agriculture by enabling real-time monitoring and control of irrigation systems. IoT devices, such as soil moisture sensors, weather stations, and smart controllers, allow farmers to make data-driven decisions about irrigation, minimizing water waste. Some examples include soil moisture sensors. These sensors measure the moisture levels in the soil and automatically adjust irrigation schedules, ensuring that crops receive the optimal amount of water without overwatering. Weather-based irrigation systems. By using weather forecasts and climate data, these systems adjust irrigation schedules based on rainfall, temperature, and humidity, further optimizing water use. Precision irrigation systems. Precision irrigation technologies, such as drip irrigation and aerial irrigation systems, focus on delivering water directly to the plant roots rather than flooding entire fields. This reduces water loss through evaporation and runoff. Some advancements include drone-assisted irrigation. Drones equipped with sensors can monitor crop health, detect areas that need irrigation, and apply water precisely where it's needed. Automated irrigation controllers. These devices allow farmers to program irrigation schedules based on specific crop requirements, soil conditions, and weather forecasts. With these innovations, smart irrigation systems are helping farmers to grow more food with less water, improving both water efficiency and crop yields. Water purification and reuse, closing the water loop. Water scarcity is not just a problem of availability, it is also an issue of water quality. Pollution from industrial, agricultural, and domestic sources has contaminated many freshwater resources. Fortunately, there are innovative technologies that are making it easier to purify and reuse water, effectively closing the water loop. Advanced filtration technologies. Innovative filtration methods are making it possible to purify water more efficiently and cost-effectively. Some of the latest advancements include nanotechnology. The use of nanomaterials for water filtration is one of the most promising innovations. Nanoparticles can remove contaminants such as heavy metals, bacteria, and viruses at a molecular level. Nanofilters are highly effective and can operate with low energy consumption. Biofiltration. Biofilters use natural biological processes to clean water. For example, constructed wetlands and biofilters utilize plants, bacteria, and microorganisms to filter out pollutants from wastewater. Water recycling and reuse. Water recycling technologies are crucial for ensuring that water is not wasted, and that treated wastewater can be used for various purposes, including irrigation, industrial use, and even drinking water. Innovations in this area include membrane bioreactors, MBRs. These combine biological treatment and membrane filtration to treat wastewater to a high standard, allowing it to be safely reused for non-potable applications. Zero liquid discharge, ZLD. ZLD is a wastewater treatment process that ensures all water is recycled and nothing is discharged into the environment. This system is being increasingly used in industrial settings to minimize water waste. Water recycling and reuse technologies can help reduce the demand for freshwater by enabling us to make the most of the water we already have. Artificial intelligence, AI, and data analytics in water management. AI and data analytics are transforming water management by providing valuable insights into how water systems operate and how they can be optimized for greater efficiency. Predictive analytics for water systems. Predictive analytics uses data, algorithms, and machine learning to forecast future water demand, detect leaks, and identify potential problems in water infrastructure. For example, leak detection. AI systems can analyze data from water networks to identify unusual patterns, such as leaks or inefficiencies in the system, allowing for faster response times and reduced water loss. Water demand forecasting. AI can predict fluctuations in water demand based on weather patterns, population growth, and seasonal variations, enabling utilities to better manage supply and reduce waste. Smart water management systems. Smart water management systems use IoT sensors, AI, and data analytics to monitor and control water distribution in real time. These systems can optimize water flow through pipelines to minimize energy use, detect leaks and reduce water loss, improve decision-making by providing detailed data on water usage and availability. The role of blockchain in water management. Blockchain technology, which provides a secure and transparent way to record transactions, is being explored for use in water management. Potential applications include water rights and distribution. Blockchain can help track the ownership and use of water rights, ensuring fair distribution and reducing conflicts over water resources. Water quality monitoring. Blockchain could create transparent and immutable records of water quality data, enabling communities to hold water providers accountable and ensure access to clean water. Blockchain's ability to create trust and transparency in water management systems could be a game changer, particularly in areas where water rights and distribution are contentious. Conclusion: a future of water innovation. As climate change and population growth place increasing pressure on global water resources, the role of technology in ensuring sustainable water management will become even more crucial. From desalination to smart irrigation, water purification to AI-powered management systems, the innovations discussed in this chapter offer hope for the future. By embracing and investing in these technologies, we can overcome the challenges of water scarcity, improve water quality, and ensure that clean water remains accessible for generations to come. Chapter 15: Global Collaborations and International Cooperation in Water Management. Water knows no borders, and neither should our efforts to protect and manage it. Water is a shared resource. Rivers, lakes, and aquifers often span multiple countries, and climate change affects the availability of water across entire regions. As water challenges grow in both scope and urgency, no single nation can address these issues alone. Instead, international cooperation and global partnerships are critical for managing the world's freshwater resources in a sustainable and equitable manner. This chapter explores the role of collaborative efforts in water management, from transboundary water treaties to global initiatives focused on water conservation, sustainability, and climate resilience. Transboundary water management, navigating shared resources. Many of the world's freshwater sources are shared by two or more countries. These transboundary waters, including rivers, lakes, and groundwater, are vital for millions of people across borders. However, managing these resources can be complex due to competing national interests, political tensions, and differing priorities regarding water use and allocation. Effective management requires collaborative frameworks that ensure equitable access and prevent conflict. The importance of transboundary agreements. To prevent disputes over shared water resources, international agreements and treaties have been established to promote cooperation and establish legal frameworks for water allocation. Some key examples include the Danube River Basin. The Danube River, one of Europe's longest rivers, flows through 10 countries. The International Commission for the Protection of the Danube River, ICPDR, established in 1998, is a regional body that works to ensure sustainable water management, pollution reduction, and ecosystem protection in the basin. The Nile Basin Initiative, NBI. The NBI is a partnership of 10 countries in northeastern Africa that share the Nile River. The initiative seeks to promote cooperative development, water management, and sustainable use of the Nile's resources, with a focus on poverty reduction, environmental sustainability, and equitable water allocation. These agreements are crucial for ensuring that countries sharing water resources cooperate rather than compete, fostering peaceful cooperation and reducing the potential for conflict over water. The role of river basin organizations. River basin organizations, RBOs, are institutions that coordinate water management across entire river basins. These organizations help ensure that water resources are managed in a way that benefits all riparian countries. RBOs typically focus on joint management of water resources, ensuring that water is allocated fairly and used sustainably across countries sharing the basin. Coordination of infrastructure projects, managing the construction and operation of dams, irrigation systems, and water treatment plants that impact multiple countries. Environmental protection, safeguarding ecosystems that depend on shared water resources, such as wetlands, aquatic biodiversity, and water quality. Examples of successful RBOs include the Indus River Commission, which manages the waters of the Indus River shared by India and Pakistan, and the Zambezi River Authority, which oversees the management of the Zambezi River Basin in southern Africa. Global water initiatives, working toward universal water access. Water access is a basic human right, yet millions of people still lack reliable access to safe drinking water and sanitation. International collaboration through global water initiatives aims to ensure that all people, regardless of location, have access to clean and affordable water. The United Nations Water Action Decade. The United Nations, UN, has long been at the forefront of global water initiatives. The Water Action Decade, 1981 to 1990, was an early UN initiative focused on addressing water-related challenges. It laid the groundwork for the Sustainable Development Goal 6 Sudanese pounds, which calls for universal access to water and sanitation by 2030. To achieve 6 Sudanese pounds, the UN promotes international cooperation through various programs, including the UN Water Partnership. This global network brings together UN agencies, governments, and civil society organizations to coordinate efforts in water management, conservation, and sanitation. The World Water Assessment Program, WWAP. WWAP monitors and reports on the state of global water resources, providing essential data for informed decision-making at the national and international levels. Global Framework for Water Scarcity, WASH. This initiative focuses on improving water access, sanitation, and hygiene, WASH, to ensure healthier communities worldwide. These efforts help mobilize resources, provide technical expertise, and foster collaboration across borders to address water challenges on a global scale. The role of non-governmental organizations, NGOs. In addition to governmental efforts, non-governmental organizations, NGOs, play a vital role in advancing global water initiatives. Many NGOs work at the grassroots level, providing clean water access, promoting sanitation, and advocating for water rights. Notable examples include Water.org, founded by Gary White and Matt Damon. Water.org works to provide access to clean water and sanitation to communities in need, using innovative financing models like microloans to help people build water and sanitation infrastructure. The Water Project. This NGO focuses on providing sustainable water solutions in sub-Saharan Africa, building wells, rainwater harvesting systems, and sanitation facilities to improve health outcomes. NGOs often act as bridges between local communities and international donors, ensuring that global efforts are grounded in the needs and realities of those most affected by water challenges. Climate change and global water security. Climate change is one of the greatest threats to global water security. Rising temperatures, altered precipitation patterns, and extreme weather events are already affecting water availability, especially in already water-scarce regions. To address these challenges, global cooperation is necessary to build resilience and protect water resources in the face of climate change. The Paris Agreement and water. The Paris Agreement, adopted by nearly every country in 2015, is a legally binding international treaty that focuses on combating climate change. Although the Paris Agreement does not specifically target water, it recognizes that water security is essential for sustainable development and climate resilience. Countries are encouraged to consider the impact of climate change on water resources and incorporate water management strategies into their national climate action plans, NDCs. For example, countries facing extreme droughts or floods may need to include strategies for improving water storage, enhancing water conservation, and protecting freshwater ecosystems as part of their climate commitments. Cross-border climate adaptation efforts. In addition to climate mitigation, global cooperation is critical for adaptation efforts that address the impact of climate change on water resources. Collaborative initiatives, such as climate adaptation partnerships and resilience-building programs, help countries share knowledge, expertise, and technologies to cope with the changing water cycle. These efforts can include shared water storage, collaborating on the construction and management of reservoirs, dams, and groundwater recharge systems to ensure a stable water supply during periods of drought. Water efficiency technologies, sharing innovations in water-saving technologies, such as smart irrigation systems and water recycling, to help countries adapt to the changing climate. Climate-resilient agriculture, working together to promote water-efficient farming practices that can withstand the impacts of changing rainfall patterns. The role of private sector and corporate responsibility. In addition to governments and NGOs, the private sector also has an important role to play in water management. Corporate responsibility in water use and management is becoming increasingly critical, particularly in industries such as agriculture, manufacturing, and energy. Companies are being encouraged to reduce water use, implementing water-efficient technologies and practices to reduce water consumption in industrial processes and manufacturing. Invest in water conservation projects, supporting local or global water initiatives that improve water access and quality, particularly in regions facing water scarcity. Adopt water stewardship principles. Companies are increasingly focusing on responsible water use by adopting water stewardship frameworks that guide their water management practices and support sustainable development. Collaborations between the private sector, governments, and NGOs can help drive innovation and scale up water conservation efforts, benefiting both businesses and local communities. Conclusion: the path toward global water security. Addressing global water challenges requires collaboration across borders, sectors, and levels of government. From transboundary water management to climate adaptation and corporate responsibility, international cooperation is key to ensuring that water resources are managed sustainably, equitably, and efficiently. As we move forward, the need for global partnerships and collective action will only grow. Water knows no borders, and neither should our efforts to protect and manage it. By working together, we can build a water-secure future for all, ensuring that clean and safe water is available for generations to come. Chapter 16: The Role of Technology in Global Water Management. In the age of innovation, technology holds the key to unlocking sustainable solutions to our global water crisis. As the world faces increasing pressure on freshwater resources due to climate change, population growth, and industrial demands, technology has become a cornerstone in the drive for sustainable water management. New technologies are making it possible to optimize water use, improve water quality, and monitor water resources more efficiently than ever before. This chapter explores the role of emerging technologies in transforming global water management, from smart water systems to innovative desalination techniques, and how these technologies can be harnessed to address the world's growing water challenges. Smart water systems, the Internet of Things, IoT, and automation. The advent of the Internet of Things, IoT, has opened up new possibilities for smart water systems. IoT refers to the network of physical devices, such as sensors, meters, and control systems, that are connected to the internet and capable of collecting and exchanging data. In water management, IoT technologies allow for real-time monitoring of water systems, providing valuable insights into water quality, demand, and infrastructure health. Real-time monitoring of water usage. IoT sensors installed in water pipes, reservoirs, and treatment plants can collect real-time data on water usage and system performance. By transmitting this data to central databases, water utilities can monitor consumption patterns. By analyzing data on water usage, utilities can better understand peak demand times and identify areas where water is being wasted. Detect leaks. IoT sensors can identify leaks in water distribution networks almost instantly, enabling faster repair and reducing water loss. Improve efficiency. Automation allows for the optimization of water flow and pressure in pipes, reducing energy consumption and improving system performance. For example, smart water meters can provide consumers with feedback on their water usage, allowing them to make more informed decisions about conservation. Utilities can also use this data to set dynamic pricing models that encourage water-saving behaviors. Predictive analytics for water infrastructure. By integrating data from IoT sensors into predictive analytics systems, water utilities can forecast potential problems before they occur. Predictive maintenance tools help detect faults in pipes, pumps, and treatment plants, allowing for proactive repairs and reducing downtime. This approach is becoming increasingly important for managing aging infrastructure, especially in developing regions where water systems are under significant strain. Artificial intelligence and machine learning in water management. Artificial intelligence, AI, and machine learning are revolutionizing water management by enabling advanced data analysis, predictive modeling, and decision-making. AI-powered systems can analyze vast amounts of data to optimize water use, improve efficiency, and predict future demand, creating more responsive and resilient water management systems. AI for optimizing water treatment. AI can enhance water treatment processes by monitoring water quality. AI-powered systems can analyze water quality data in real time, detecting contaminants such as bacteria, heavy metals, or chemicals, and adjusting treatment processes accordingly. Optimizing chemical dosing. AI algorithms can fine-tune the amount of chemicals, e.g., chlorine or coagulants, used in water treatment, reducing waste and ensuring that water is treated to the required standards while minimizing the environmental impact. Predicting treatment needs. Machine learning models can forecast the water treatment needs based on historical data, weather patterns, and seasonal changes, helping utilities prepare for varying water quality conditions. AI-based solutions can also improve water desalination and filtration by automating adjustments to filtration systems, maximizing efficiency, and reducing energy costs. Machine learning for water conservation. In agriculture, machine learning is being used to improve irrigation practices and optimize water use. By analyzing data from soil moisture sensors, weather forecasts, and crop requirements, machine learning models can automate irrigation. Machine learning systems can automatically adjust irrigation schedules, applying the right amount of water at the right time, depending on the moisture levels in the soil and upcoming weather conditions. Predict crop water needs. By analyzing crop types, weather data, and soil characteristics, machine learning can predict how much water each crop needs, helping farmers minimize water usage while maximizing yields. These AI and machine learning systems are not only improving efficiency, but also promoting sustainable agricultural practices, which are essential for reducing water waste in one of the largest global water-consuming sectors. Desalination technologies, turning saltwater into freshwater. As freshwater supplies become increasingly strained, desalination has emerged as a critical solution for providing clean drinking water, especially in coastal regions. Desalination technologies, which remove salt and other impurities from seawater, have been in use for decades, but recent advancements are making them more efficient, cost-effective, and sustainable. Reverse osmosis, a key technology. The most widely used desalination method is reverse osmosis, RO, where seawater is forced through a semi-permeable membrane that filters out salt and other contaminants. While RO desalination is effective, it is energy-intensive, and its environmental impact can be significant. Recent innovations have sought to reduce the energy consumption of RO systems. Energy recovery devices. These devices capture and reuse the energy produced during the desalination process, reducing the overall energy demand. Low-energy membranes. New materials, such as graphene-based membranes, are being developed to improve the efficiency of RO by allowing water molecules to pass through more easily while blocking larger salt ions. Solar-powered desalination. In regions with abundant sunlight, solar desalination plants use solar energy to power the desalination process, reducing reliance on fossil fuels and lowering greenhouse gas emissions. Alternative desalination methods. Beyond reverse osmosis, several alternative desalination methods are being explored. Electrodialysis. This method uses electrical charges to separate salts from water through ion exchange membranes. While it is more energy efficient than traditional RO, it is better suited for brackish water than seawater. Forward osmosis, a newer desalination technique. Forward osmosis uses a semi-permeable membrane to allow water to pass through but leave salt and other impurities behind. This method has the potential to be less energy-intensive than reverse osmosis. These innovations aim to make desalination a more sustainable solution to global water scarcity, especially in arid regions. Blockchain technology, ensuring transparency and accountability. Blockchain technology, most commonly associated with cryptocurrencies, has potential applications in water management as well. Blockchain's secure and transparent nature makes it an ideal tool for ensuring accountability and trust in water management systems. Tracking water usage and distribution. Blockchain can be used to create transparent systems for tracking water rights, usage, and distribution, ensuring that water resources are allocated fairly. In regions with limited access to water, blockchain-based systems can help ensure that water rights are honored and that water is distributed equitably. Smart contracts. Blockchain enables the use of smart contracts that automatically execute transactions when certain conditions are met. For example, a smart contract could automatically release funds for water-related projects once certain milestones are reached, such as the construction of a water treatment facility. Water quality certification. Blockchain can also be used to ensure that water quality standards are met. By recording data on water treatment and purification processes, blockchain can create a transparent, immutable record of water quality that can be accessed by consumers and regulators alike. Promoting water stewardship. In addition to improving water governance, blockchain can help promote corporate water stewardship. Companies can use blockchain to prove their commitment to sustainable water use by publicly sharing data on their water consumption, water sourcing, and water treatment practices. This transparency can increase trust with consumers and investors while encouraging responsible water use. Water purification and recycling technologies. Advancements in water purification and recycling technologies are key to ensuring that water is used as efficiently as possible, especially in regions facing chronic water scarcity. New technologies are improving our ability to treat wastewater and reuse it safely, reducing the need for fresh water from natural sources. Membrane bioreactors, MBRs. Membrane bioreactors, MBRs, combine biological treatment with membrane filtration to produce high-quality effluent that can be reused in non-potable applications, such as irrigation or industrial processes. MBRs are being used in both developed and developing countries to treat wastewater more efficiently and reduce the environmental impact of sewage disposal. Advanced filtration technologies. New filtration technologies, such as nanotechnology-based filters and activated carbon filtration are making it easier to remove contaminants from water, including heavy metals, pathogens, and microplastics. These technologies allow for the safe reuse of treated wastewater, especially in agriculture, industry, and even for drinking water in some cases. Conclusion: harnessing technology for a sustainable water future. Technology has the potential to transform how we manage, use, and conserve water, helping to address the growing challenges of water scarcity, pollution, and inefficient use. From smart water systems and AI-powered analytics to desalination and blockchain, these innovations are already making a significant impact on water management practices worldwide. As we move forward, it will be crucial to continue investing in and scaling up these technologies to ensure that water is managed sustainably and equitably for all. In the next chapter, we will explore policy frameworks and governance structures that support the adoption of these technologies and drive global water sustainability. Chapter 17: Policy and Governance for Global Water Sustainability. Water is life, and how we govern it will determine the future of our planet. Water governance is a complex and multifaceted challenge that requires effective policy frameworks and coherent institutional arrangements. From ensuring equitable access to water to promoting sustainable use and protecting freshwater ecosystems, the governance of water resources influences nearly every aspect of human life. In an era of climate change, population growth, and rising water scarcity, strong governance and well-designed policies are essential for achieving global water sustainability. This chapter explores the policies, legal frameworks, and governance structures that can guide the management of water resources in a changing world. The importance of water governance. Water governance refers to the way in which decisions are made regarding the management, allocation, and protection of water resources. It encompasses both formal policies and informal practices, and involves a range of stakeholders, including governments, local communities, private entities, and international organizations. Good water governance ensures that water is managed in a way that is equitable, ensuring all people have access to safe and affordable water. Sustainable, balancing present and future water needs, conserving ecosystems, and reducing pollution. Transparent and accountable, promoting open decision-making and holding actors accountable for their actions. Inclusive, ensuring that all stakeholders, including marginalized groups, have a voice in water management decisions. Effective governance structures are crucial for addressing the increasing water challenges associated with climate change, urbanization, and agricultural demands. Integrated Water Resources Management, IWRM, has emerged as a key framework for balancing these competing needs and managing water resources holistically. Integrated Water Resources Management, IWRM. Integrated Water Resources Management, IWRM, is an approach to water governance that considers the entire watershed or river basin, recognizing that water systems are interconnected and that all aspects of water management, social, economic, and environmental, must be considered. IWRM emphasizes the importance of collaboration, engaging all stakeholders in the decision-making process, including governments, the private sector, communities, and civil society organizations. Sustainability, managing water resources in a way that meets the needs of the present without compromising the ability of future generations to meet their own needs. Equity, ensuring that all groups, especially the most vulnerable, have access to adequate and clean water. Efficiency, using water resources in a way that maximizes benefits while minimizing waste and pollution. The IWRM framework has been adopted by many countries around the world, guiding national and local water management policies. However, implementation remains challenging, especially in regions where governance structures are weak or fragmented. The challenges of implementing IWRM. While IWRM offers a comprehensive and holistic approach, its implementation can be difficult due to several factors. Fragmented governance. In many countries, water management is divided among multiple agencies and levels of government, making coordinated action difficult. Competing priorities. Conflicting demands for water, such as irrigation, industrial use, and domestic supply, can make it difficult to find a balance that satisfies all stakeholders. Limited data and monitoring. Effective water management requires accurate data on water availability, quality, and usage. In many regions, data is insufficient or unreliable, making it hard to make informed decisions. Despite these challenges, IWRM remains a powerful tool for ensuring that water resources are managed in a way that benefits all sectors of society, promotes long-term sustainability, and protects the environment. Water laws and regulations. Legal frameworks for protection and management. A robust legal framework is essential for the effective governance of water resources. Water laws set the rules for how water can be accessed, used, and protected, while regulations provide the detailed procedures for enforcing these laws. Water laws can include water rights. These laws govern how water is allocated among users, ensuring that the needs of different sectors, agriculture, industry, domestic use, etc., are met while protecting the rights of marginalized communities. Water quality standards. Regulations that set limits on pollutants in water bodies and establish procedures for monitoring water quality. Environmental protection. Laws that protect critical ecosystems, such as wetlands and watersheds, and ensure that water use does not degrade the environment. Climate resilience. Laws that integrate climate change adaptation into water management, such as guidelines for the construction of flood defenses or measures to protect water sources from drought. Water rights and access. One of the most fundamental issues in water governance is determining how to allocate water among competing users. Water rights systems vary widely around the world, with some countries using a riparian rights system where water rights are based on land ownership along a watercourse, while others use a prior appropriation system where rights are granted based on first use. In many parts of the world, water scarcity has led to tensions over water rights, especially in transboundary river basins, where countries must negotiate how to share limited water resources. Establishing equitable and transparent water rights systems is essential for preventing conflict and ensuring that water is distributed fairly. The role of international water treaties and agreements. Many of the world's freshwater resources are shared by multiple countries, which requires cooperation to avoid conflicts and ensure equitable and sustainable use. International water treaties and agreements play a critical role in managing transboundary water resources, such as rivers, lakes, and aquifers. The UN Watercourses Convention. The United Nations Watercourses Convention, 1997, is a key international agreement that provides a framework for the sustainable use and protection of transboundary water resources. It outlines principles for equitable and reasonable use, ensuring that countries share the benefits of transboundary waters fairly, taking into account their respective needs and interests. No harm, preventing one country from causing significant harm to the water resources of another. Cooperation, encouraging countries to cooperate in the joint management of shared water resources. The Convention promotes dialogue and cooperation between nations, helping to reduce the potential for conflict and ensuring that shared water resources are managed sustainably. Regional water agreements. In addition to global frameworks like the UN Watercourses Convention, many regions have developed their own regional water agreements to manage shared water resources. Some notable examples include the Nile Basin Initiative, NBI, a partnership of 10 countries in northeastern Africa that share the Nile River, working together to promote cooperative water management and development. The Mekong River Commission, MRC, a regional organization that fosters cooperation among countries in Southeast Asia, Cambodia, Laos, Thailand, and Vietnam that share the Mekong River. The Indus Water Treaty, a treaty between India and Pakistan that governs the allocation of water from the Indus River, one of the world's most contentious transboundary water basins. These regional agreements play a critical role in ensuring that countries cooperate rather than compete over shared water resources, thereby promoting peace and sustainable water management. Strengthening institutional frameworks for water management. Strong water institutions are necessary to manage water resources effectively, enforce laws, and ensure that water policies are implemented. These institutions must be equipped with the necessary resources, expertise, and authority to carry out their responsibilities. National water agencies. National water agencies are responsible for managing water resources at the country level. These agencies may be responsible for water supply and sanitation, ensuring that clean and safe water is available for all people. Flood and drought management, implementing measures to mitigate the impacts of extreme weather events on water resources. Water quality monitoring, ensuring that water resources meet required quality standards. Policy development, crafting water policies and regulations that align with national development goals and international commitments. Strengthening these institutions and ensuring they have the capacity to implement policies and regulations is key to achieving water security. Multi-level governance. Water governance often involves multiple levels of decision-making, from local to national to international. Effective multi-level governance is critical for ensuring that water resources are managed in a way that meets the needs of both local communities and broader national or global objectives. This requires strong coordination between governments, the private sector, and local stakeholders, ensuring that decisions are made at the appropriate scale and that there is accountability at every level. Conclusion: the path forward for water governance. As water challenges continue to grow, the need for strong governance structures and effective policies has never been more urgent. By implementing integrated water management strategies, strengthening water laws and regulations, fostering international cooperation, and ensuring the capacity of water institutions, we can move toward a future where water is managed sustainably, equitably, and efficiently. Water governance is not only about managing a resource, it's about ensuring the health, well-being, and prosperity of future generations. In the next chapter, we will explore the role of community-based water management and how local communities can play a central role in water sustainability. Chapter 18: Community-based water management. When communities are empowered to manage their water resources, they become the architects of their own resilience. Water is at the heart of every community, and how water is managed affects everything from public health to economic development. In an era of climate change and growing water scarcity, community-based water management, CBWM, has emerged as a powerful model for addressing local water challenges. Unlike top-down management approaches, which often overlook local knowledge and needs, community-based approaches focus on empowering local people to take an active role in the planning, decision-making, and stewardship of their water resources. In this chapter, we explore how community-based water management is reshaping the way we think about water governance, the benefits of localized solutions, and the challenges and successes of implementing community-driven water initiatives. We'll also examine the role of social capital, local knowledge, and participatory decision-making in building water resilience and promoting long-term sustainability. What is community-based water management? Community-based water management, CBWM, is an approach that emphasizes local participation, empowerment, and collaborative decision-making in the management of water resources. The model encourages local communities to take the lead in water-related initiatives, fostering greater ownership, accountability, and responsiveness to local needs. Key elements of CBWM include local control and decision-making. Communities have the authority to make decisions about how water resources are allocated and managed within their boundaries. Participatory governance. Decision-making processes actively involve all community members, ensuring that the voices of marginalized and vulnerable groups are heard. Sustainability and resilience. CBWM aims to manage water resources in a way that ensures long-term sustainability, addressing both current needs and future challenges. Rather than being imposed from above by governments or external agencies, CBWM is a bottom-up approach where the community has a central role in the design, implementation, and monitoring of water management practices. The importance of local knowledge and social capital. One of the most significant advantages of community-based water management is the use of local knowledge. Communities living in a particular region often have deep, generational knowledge about their water resources, ecosystems, and the challenges they face. This knowledge is invaluable for managing water systems in a way that is both sustainable and context-specific. Local knowledge. Local communities often understand the hydrological cycles, seasonal variations, and water quality of their environment better than external experts. This indigenous knowledge can be used to assess local water needs. Communities are best positioned to assess their own water requirements, including the quantity and quality of water needed for domestic use, agriculture, and industry. Monitor water resources. Local populations are often more aware of changes in water sources, such as the drying up of a well, the onset of contamination, or shifts in water availability. Develop adaptive strategies. Communities can leverage traditional practices and knowledge to develop resilient strategies for managing water, particularly in response to climate change. By integrating local knowledge with scientific data, CBWM initiatives can help develop more accurate, relevant, and adaptable water management practices. Social capital and collective action. Social capital refers to the networks, norms, and trust that exist within communities, which are essential for cooperation and collective action. Strong social capital is crucial for the success of CBWM, as it fosters collaboration among community members and with external partners such as governments, NGOs, and the private sector. Key aspects of social capital in water management include trust and cooperation. Effective water management requires a high degree of trust between community members, which ensures that resources are shared fairly and that collective action is taken when needed, e.g., repairing infrastructure, managing water sources. Inclusive participation. Social capital also means ensuring that all community members, including women, youth, and marginalized groups, are included in decision-making processes. Gender equality is particularly important in water management, as women often bear the primary responsibility for water collection and use in many communities. Social networks. Strong local networks, including water user associations or local councils, help communities organize, mobilize resources, and solve problems collectively. In communities with high levels of social capital, water management initiatives are more likely to succeed because people are willing to work together to protect and conserve their water resources. Benefits of community-based water management. The benefits of community-based water management are far-reaching, not only in terms of water security, but also for broader community development. Some key benefits include enhanced water access and equity. In many parts of the world, water scarcity is exacerbated by inequalities in water access. CBWM ensures that local populations have a say in how water is allocated, leading to more equitable outcomes. By involving communities in decision-making, the needs of all members, particularly marginalized groups, are more likely to be addressed. Local prioritization. Community members can prioritize water needs based on urgency, ensuring that those with the greatest need, e.g., vulnerable populations, women, or marginalized groups, are served first. Cost-effective solutions. Localized solutions can be more affordable and appropriate than large-scale infrastructure projects, making it easier for communities to access clean water without incurring significant costs. Increased resilience to climate change. Water systems managed at the community level are often better able to adapt to the impacts of climate change. Local communities are often more attuned to climate-related risks, such as droughts, floods, or water pollution, and are better positioned to implement adaptive measures. Climate adaptation. Communities can develop locally tailored strategies to deal with changing precipitation patterns, reduce water wastage, and improve water storage during dry seasons. Sustainable practices. CBWM encourages the adoption of sustainable water practices such as rainwater harvesting, wastewater recycling, and the use of drought-resistant crops in agriculture. This adaptive capacity is crucial for building climate resilience, especially in areas that are vulnerable to extreme weather events. Empowerment and social cohesion. When communities take charge of their water resources, they gain a sense of ownership and pride in their water systems. This empowerment leads to stronger social cohesion and a greater sense of responsibility for the environment. Leadership development. CBWM fosters the development of local leadership, particularly among women and youth, empowering them to become active participants in governance and decision-making processes. Community mobilization. A sense of ownership over water resources often leads to more effective community mobilization for conservation efforts and infrastructure maintenance. Social cohesion and collective action make communities more resilient not only to water-related challenges, but also to other socioeconomic issues. Examples of successful community-based water management initiatives. Many communities around the world have successfully implemented community-based water management initiatives, often with the support of local governments, NGOs, and international agencies. These examples demonstrate how CBWM can be adapted to different cultural, geographical, and socioeconomic contexts. The Water User Associations in Nepal. In Nepal, water user associations, WUAs, are local organizations that manage water resources for irrigation. These associations have been instrumental in improving water access for smallholder farmers in rural areas. By empowering communities to manage their own water resources, WUAs have increased water use efficiency, reduced conflicts over water allocation, and improved agricultural productivity. The Chilambulu Water Supply Project in Zambia. In Zambia, the Chilambulu Water Supply Project is an example of successful community-based water management in rural areas. The project involves local communities in the planning, construction, and maintenance of water supply systems. By training community members to operate and maintain the systems, the project has improved water access, reduced waterborne diseases, and created local employment opportunities. Rainwater harvesting in India. In India, many villages have turned to rainwater harvesting as a sustainable solution to water scarcity. The Rajasthan region, for example, has seen significant success in using traditional rainwater harvesting techniques, such as khans, small circular reservoirs, and johads, check dams. These techniques help conserve rainwater for agricultural and domestic use, reducing dependence on external water sources. Challenges to community-based water management. While CBWM offers significant benefits, it also faces challenges. Capacity building. Many communities may lack the technical knowledge or resources to manage complex water systems effectively, requiring external support for training and infrastructure development. Funding. CBWM initiatives often depend on external funding, which may be inconsistent or insufficient to sustain long-term projects. Political and institutional support. CBWM requires strong backing from local governments and institutions, which may not always be available or may conflict with central government policies. Despite these challenges, many communities continue to find innovative ways to overcome barriers and implement successful water management strategies. Conclusion: empowering communities for water sustainability. Community-based water management represents a transformative approach to water governance. By empowering local communities to take control of their water resources, we create more resilient, equitable, and sustainable water systems. In the face of climate change and water scarcity, CBWM can play a central role in adapting to new challenges, improving water access, and fostering social cohesion. Chapter 19: Water Education and Public Awareness. An informed public is the foundation of sustainable water management. Through education and awareness, we empower individuals to take action. As the world grapples with water scarcity, pollution, and the impacts of climate change on water resources, water education and public awareness have become critical tools for achieving sustainable water management. Informed communities are more likely to adopt water-conserving behaviors, engage in policy advocacy, and support effective water management practices. This chapter explores the role of education and public awareness campaigns in promoting water sustainability, with a focus on how individuals, communities, and organizations can contribute to preserving this vital resource. The role of education in water management. Water education is fundamental in shaping how individuals and communities understand, value, and manage water resources. By teaching people about the scientific principles behind water systems, the importance of water conservation, and the impacts of climate change on water availability, education helps build the knowledge base necessary for responsible water management. Formal education systems. Integrating water education into formal education systems, from primary schools to universities, ensures that future generations are equipped with the knowledge and skills to manage water sustainably. Key components of formal water education include basic water literacy, teaching students about the water cycle, the sources of fresh water, and the importance of maintaining clean water. Climate change and water, providing information about how climate change affects water systems, including changes in precipitation patterns, the risks of droughts, and the potential for flooding. Sustainable practices, educating students about sustainable water use in agriculture, industry, and households, such as using less water in irrigation or reducing water wastage. By embedding water education into the curriculum, we can create a generation that understands water challenges and is motivated to find solutions. Vocational and professional training. In addition to formal education, vocational and professional training plays a key role in building expertise in water management. This type of training is essential for water engineers. Professionals who design and maintain water systems must understand modern techniques for sustainable water use, such as low-flow irrigation or wastewater recycling. Water policy specialists, training policymakers in the complexities of water governance and the social, economic, and environmental implications of water decisions. Community leaders, empowering local leaders to educate their communities about water conservation and management practices. Such training ensures that those responsible for managing water systems, from local governments to multinational corporations, are equipped to implement sustainable solutions. Public awareness campaigns, reaching beyond the classroom. While formal education is important, public awareness campaigns are essential for reaching a wider audience. The success of any water management strategy depends not only on experts and policymakers, but also on the active participation of the general public. The power of media and communication. The media, including television, radio, newspapers, and online platforms, are powerful tools for spreading water awareness. Public service announcements, documentaries, and social media campaigns can raise awareness, informing people about the urgency of water conservation and the challenges posed by climate change. Promote water-saving behaviors, encouraging simple, everyday actions like fixing leaky faucets, reducing water waste, and adopting water-efficient appliances. Advocate for policy change, mobilizing public support for policies that prioritize sustainable water management, such as investment in water infrastructure or legal protections for water bodies. A well-targeted media campaign can inspire widespread public engagement and contribute to changing social norms around water use. Local outreach and community engagement. In addition to mass media, community outreach is a critical component of public awareness. Local communities are often more responsive to personalized information that is relevant to their daily lives. Effective outreach strategies include workshops and events, organizing public events that teach people about water conservation, the impacts of climate change, and the importance of protecting local water resources. Water conservation demonstrations, setting up hands-on displays that show how to harvest rainwater, install water-efficient fixtures, or reduce water use in agricultural practices. Local leaders as ambassadors, training influential community members, such as religious leaders, teachers, or local business owners, to act as ambassadors for water conservation in their communities. Community-driven outreach ensures that information reaches those who need it most, particularly in rural or underserved areas. The role of technology in water education and awareness. Technology plays an increasingly important role in water education and public awareness. Innovations in digital tools and platforms can help make complex water-related issues more accessible and engaging. Online platforms and mobile apps. The rise of online platforms and mobile applications provides new ways to engage the public in water education. Apps can offer users information on local water quality, real-time water usage tracking, and conservation tips. Platforms like websites, blogs, and social media accounts allow organizations to share data and information in real time, host webinars or online discussions on water issues, provide interactive tools, such as calculators for estimating household water use or assessing the carbon footprint of water consumption. Such digital tools make water education accessible to a global audience and encourage individuals to take actionable steps in their daily lives. Data visualization tools. Data visualization is another powerful tool for improving water awareness. Interactive maps, infographics, and charts can help people understand complex data on water resources, such as water scarcity, showing regions at risk of drought or over-extraction of groundwater. Water quality, highlighting areas with contaminated water sources and the effects of pollution. Climate impacts, demonstrating how changing weather patterns affect local water supplies. By presenting information in a visually engaging way, data visualization can help people better understand the challenges facing their water systems and motivate them to take action. The impact of water education on sustainable water practices. Education and awareness have a significant impact on behavioral change. When individuals understand the value of water and the consequences of overuse or pollution, they are more likely to adopt sustainable water practices. Some of the ways that education can lead to better water management include reduced water wastage. Simple actions such as turning off taps when not in use, using water-efficient appliances, or reducing irrigation in agriculture can collectively make a significant difference in water use. Water pollution prevention. Educated individuals are more likely to avoid behaviors that contribute to water pollution, such as disposing of chemicals or waste in rivers and lakes. Community-led water initiatives. Informed communities are better able to organize water-saving projects, such as rainwater harvesting, watershed restoration, or cleaning up local water bodies. Water education is the key to fostering a culture of conservation, where individuals understand that every drop counts and that their actions can help secure water for future generations. The challenges of water education and public awareness. While water education and public awareness are critical, there are challenges to achieving wide-scale success. Lack of resources. Many communities, especially in developing countries, lack the resources or infrastructure to implement comprehensive water education programs. Cultural barriers. In some regions, there may be cultural resistance to new water practices, or a lack of awareness about the importance of water conservation. Competing priorities. In areas with limited resources, water education may not be prioritized over other pressing issues like healthcare, education, or economic development. To overcome these challenges, water education and awareness campaigns must be context-sensitive, locally relevant, and engage multiple stakeholders, including governments, NGOs, and the private sector. Conclusion: a call for action. Water education and public awareness are essential tools in the fight for water sustainability. By educating people and raising awareness about the importance of water, we can foster a global culture of conservation and responsible water use. The more people understand the complexities of water systems and the impacts of climate change, the more likely they are to take action, both individually and collectively, to ensure that water resources are managed in a way that benefits all people and the planet. In the next chapter, we will examine innovative water technologies that can support sustainable water management and help us overcome the challenges posed by climate change. Chapter 20: Innovative Water Technologies. Innovation is the key to unlocking sustainable water solutions in a world challenged by scarcity and climate change. As the planet faces escalating water stress due to population growth, climate change, and environmental degradation, innovative water technologies are increasingly seen as essential tools for ensuring water security. From desalination plants to smart irrigation systems, technological advancements are transforming how we access, use, and conserve water. These innovations are not only improving efficiency, but are also helping to make water management more resilient to the challenges of a changing climate. This chapter explores the latest technological solutions in water management, from water purification technologies to advanced irrigation systems, and discusses how these innovations are shaping the future of water sustainability. Water purification and desalination. Access to clean water remains one of the greatest challenges for many communities around the world. Traditional sources of freshwater are being depleted, and contamination from industrial and agricultural practices continues to pollute existing water resources. Water purification technologies and desalination are two critical innovations that are helping to address these challenges. Water purification technologies. Water purification technologies are designed to remove contaminants from water, making it safe for human consumption, agricultural use, and industrial processes. Several cutting-edge technologies are currently in use or being developed. Reverse osmosis, RO, one of the most widely used purification methods. RO forces water through a semi-permeable membrane to remove salts, heavy metals, and other impurities. RO is commonly used in both residential and industrial water treatment. UV water purification. Ultraviolet UV light is used to kill or deactivate harmful microorganisms, including bacteria, viruses, and protozoa, without the use of chemicals. This technology is becoming more popular for household and small-scale water purification. Graphene-based filtration. Graphene, a single layer of carbon atoms arranged in a hexagonal lattice, is being used in the development of highly efficient filtration systems. Graphene filters are able to remove even the smallest contaminants, making them promising for future water purification technologies. Electrocoagulation. This process uses electrical currents to remove pollutants such as heavy metals, suspended solids, and oils from water. It is particularly useful for treating industrial wastewater. These technologies are already helping to provide clean water to millions of people in water-scarce areas. However, many of these systems require high energy inputs or have high maintenance costs, which can limit their widespread adoption in developing regions. As research continues, more energy-efficient and cost-effective purification methods are expected to emerge. Desalination. Desalination is the process of removing salts and other impurities from seawater, making it suitable for human consumption and agricultural use. Given that approximately 97% of the Earth's water is saltwater, Desalination has the potential to significantly increase the availability of fresh water. Reverse osmosis desalination. Reverse osmosis, RO, is the most common method used in desalination plants. Despite its energy-intensive nature, improvements in energy efficiency have made RO desalination more viable in recent years. Multi-effect distillation, MED. MED is another desalination technique where seawater is evaporated and condensed multiple times to extract freshwater. This method is more energy efficient than traditional distillation. Forward osmosis. Forward osmosis is a promising new desalination technology that uses natural osmotic pressure to draw water through a membrane, reducing the need for high-energy input. Desalination is an important option for countries with limited access to freshwater, especially those located in arid regions or with large coastal areas. However, the high energy requirements and environmental impacts of desalination, including brine disposal, present challenges that need to be addressed. Smart irrigation technologies. Agriculture is one of the largest consumers of water globally, accounting for approximately 70% of freshwater use. As climate change alters rainfall patterns and water resources become scarcer, smart irrigation technologies are offering solutions that allow farmers to irrigate crops more efficiently and sustainably. Drip irrigation. Drip irrigation is a highly efficient method that delivers water directly to the roots of plants through a system of tubes and emitters. This minimizes water loss due to evaporation or runoff and ensures that water is used only where it is needed. Automated drip irrigation. Advances in automation allow drip irrigation systems to adjust water delivery based on real-time data about soil moisture, weather conditions, and crop needs. Smart sensors. Soil moisture sensors and weather stations integrated with irrigation systems help farmers optimize water use. These sensors can detect when the soil is dry and automatically activate the irrigation system, preventing overwatering and underwatering. Drip irrigation not only conserves water, but also improves crop yields by ensuring plants receive consistent moisture, which is especially important in areas with unreliable rainfall or water scarcity. Precision irrigation. Precision irrigation uses advanced technologies like sensors, GPS, and data analytics to provide the right amount of water at the right time and place. Some examples of precision irrigation technologies include variable rate irrigation, VRI. VRI allows farmers to adjust irrigation rates based on the specific needs of different areas within a field. For example, parts of a field with more fertile soil might require less water than other areas, reducing overall water consumption. Drones and satellites. Drones equipped with imaging sensors can capture data on crop health, moisture levels, and soil conditions. Satellite imagery can also be used to monitor large-scale irrigation systems, ensuring they are operating efficiently. These precision technologies can significantly reduce water waste in agriculture while maintaining or even increasing crop productivity. Water recycling and reuse technologies. Water recycling and reuse technologies allow wastewater to be treated and returned to the system for non-potable or even potable uses. These technologies are particularly important in urban areas where water demand is high and freshwater sources are limited. Wastewater treatment and reuse. Membrane bioreactors, MBRs. MBRs combine biological filtration with membrane filtration to treat wastewater efficiently. This technology allows for the reuse of treated wastewater for irrigation, industrial processes, and even potable uses in some cases. Greywater recycling. Greywater is wastewater from sinks, showers, and washing machines that can be treated and reused for non-potable purposes such as irrigation and flushing toilets. Systems for greywater recycling are becoming increasingly popular in households and businesses looking to conserve water. Water purification for potable use. In some cities, treated wastewater is further purified using advanced filtration technologies, such as reverse osmosis, to produce potable water. This approach is being adopted in water-scarce regions, such as Singapore's Any Water initiative, which treats and reuses wastewater for drinking. By recycling and reusing water, cities and industries can reduce their reliance on freshwater sources, making them more resilient to water shortages and climate change. Digital technologies and water management. Advances in digital technologies are enabling smarter, more efficient water management systems. These technologies harness the power of data, artificial intelligence, and the Internet of Things, IoT, to optimize water use and improve the resilience of water systems. Smart water meters. Smart water meters are digital devices that track water usage in real time, providing detailed insights into consumption patterns. These meters can help consumers monitor their water use and identify areas where they can reduce consumption, enable utility companies to detect leaks and inefficiencies in water distribution systems more quickly, provide valuable data that can inform water management policies and improve the allocation of resources. Smart water meters are increasingly being used in urban areas to improve water efficiency and reduce wastage. Artificial intelligence and data analytics. Artificial intelligence, AI, and data analytics are being used to analyze vast amounts of data from water management systems, weather forecasts, and consumer usage patterns. This enables more informed decision-making and the development of predictive models for water availability and demand. Predictive analytics can forecast future water shortages based on climate patterns, population growth, and water usage trends. AI-driven optimization can help utilities manage water distribution networks more efficiently, reducing waste and improving service delivery. By using AI and data analytics, water managers can make more accurate, timely decisions, improving the efficiency and sustainability of water systems. The future of water technologies. The future of water management will depend on the continued development and deployment of innovative technologies. As we confront the challenges of climate change, population growth, and water scarcity, these technologies will play a critical role in ensuring a sustainable and equitable water future. Key trends in future water technologies include decentralized water systems, small-scale local water treatment and distribution systems that can reduce reliance on large centralized infrastructure. Artificial wetlands and nature-based solutions, leveraging the natural filtration and purification capabilities of ecosystems like wetlands, forests, and riparian zones to treat and manage water. Advanced desalination, new desalination methods that are more energy efficient and environmentally sustainable, such as forward osmosis or renewable energy-powered desalination plants. Innovation in water technologies holds immense potential, but it is crucial that these technologies are accessible and affordable, particularly for underserved communities in developing countries. Conclusion: innovation as the key to water sustainability. Innovative water technologies are providing new ways to address the growing challenges of water scarcity, contamination, and climate change. From desalination plants to smart irrigation systems, these technologies offer hope for a future where water resources are managed more efficiently and sustainably. However, for these technologies to be successful, they must be coupled with sound governance, robust policy frameworks, and global collaboration. Epilogue: the path forward. As we stand at the crossroads of climate change and water management, the future of our planet depends on the choices we make today. From policy innovations to technological breakthroughs, the tools we have at our disposal offer unprecedented opportunities to address the mounting challenges of water scarcity, contamination, and climate impacts. Yet the path forward is not just about adopting new technologies or developing new policies. It is about creating a global culture of water stewardship that recognizes the essential role water plays in sustaining life, ecosystems, and economies. In the chapters of this book, we have explored the science of water systems, the effects of climate change on water resources, the importance of sustainable water management, and the innovative technologies that are reshaping how we use, conserve, and protect water. We have also delved into the role of education, public awareness, and policy frameworks in ensuring that these solutions are effectively implemented and embraced by communities worldwide. However, one central truth remains. Water is not just a resource, it is the lifeblood of our planet. The delicate balance between human needs, environmental health, and economic development hinges on how we manage this precious resource. In a world where water stress and climate-related disruptions are increasingly common, it is crucial that we act with urgency, collaboration, and foresight. The call for action. The challenges we face in managing water resources are vast, but so are the opportunities. By working together, governments, businesses, communities, and individuals, we can ensure a future where access to clean, safe water is no longer a privilege, but a right for all. This future requires bold policy changes. Governments must prioritize water security, adopting comprehensive policies that support sustainable water management, improve infrastructure, and protect ecosystems. Technology for good. We must harness the potential of innovative water technologies, from desalination and smart irrigation to water recycling and purification, to optimize the use of every drop. Education and awareness. As individuals, we all play a part in water conservation. It is critical to continue raising awareness, educating the public, and inspiring behavioral changes that contribute to a culture of conservation. Global collaboration. Water knows no borders. The challenges we face are shared by people around the world. Collaboration between nations, organizations, and local communities is essential to ensure that all have equitable access to clean water, regardless of geography or income. The road ahead may be challenging, but it is not without hope. The incredible resilience of communities, the power of innovation, and the strength of collective action give us the tools we need to safeguard water for future generations. Now is the time to act, to innovate, and to collaborate, before the challenges become insurmountable. A vision of the future. Imagine a world where every person, no matter where they live, has access to clean, reliable water. Where farmers use smart irrigation to grow crops with minimal water waste, and cities are powered by energy-efficient desalination plants that provide safe drinking water. In this future, natural ecosystems such as wetlands and forests are restored, playing their part in filtering water and regulating its flow. Communities across the globe work together to manage water resources, taking collective responsibility for ensuring that this vital resource is available for generations to come. This vision is not a far-off dream. It is a vision we can achieve if we make the necessary changes today. Closing thoughts. Water is a shared resource that connects us all, whether we are in bustling urban centers, remote rural communities, or the vast oceans of the world. As the climate continues to change and the pressures on our water systems intensify, it is more important than ever to embrace a sustainable, inclusive, and innovative approach to water management. Together, we can create a world where water is managed wisely, where access to clean water is guaranteed for all, and where our natural ecosystems thrive alongside human development. The time for action is now. Let us rise to the challenge and ensure that future generations inherit a world where water sustains, nourishes, and empowers. About the author. Olubusayo Aina is the director of LAREINS, an energy, climate, ESG, and sustainability training institution. He is also a professor with the Global Humanistic University, GHU, in Anguilla. Olubusayo has a PhD in energy economics and finance.